No. Okay, so we'll start in a minute or two, but maybe the people online could already confirm that they can hear me. That would be convenient and reassuring. Okay, excellent, thank you. All right, let's give it one more minute and then get started. Okay, so let's get started. So welcome to this training. This is organized in collaboration with Flemish Supercomputing Center on the one hand, VSC, and with USC Belgium on the other hand. So this is an international training. I'm not using my own slides, so Rolf Rabentzeifer is not me, unfortunately, because then I would be a lot smarter than I am. But he is someone who works at HLRS, as you can see on the title slide. And back in the day, so in, I don't quite remember, 2010 or 2012, I don't quite recall, there was an interesting initiative by Rolf, Train the Trainer program. So basically you could attend one of his trainings as a trainee trainer. Okay, this gets involved. And basically he showed you how to do these kind of trainings, and I try to more or less do it the way he does that. I wanted to do that at the time because I thought, okay, we need a training on MPI, we need training on OpenMP, and this was a praise training, so I thought, okay, this should be quite high level, and indeed it was. It was quite an interesting experience for me because I had very little experience with MPI at that time, and Rolf really goes into the nitty-gritty details, so I also had to help the people in the training. So I had to prepare in the evening in order for the material which would be covered the next day and so on. So it was pretty intense, but rather interesting. So I didn't have to actually create my own training material as I had feared because it's pretty huge, but I can use a training material that Rolf provides. And although he's retired now, he still is on the one hand giving trainings and on the other hand still updating this material. So that's quite nice and quite convenient for me. Because as you will see, there is 523,750,000, etc. slides. If you have to build such a slide deck, it takes years. And indeed, of course, obviously, it has taken years, only not my years, but Rolf's. So the slide deck goes back to the start of the century, I think, when Rolf started creating the first MPI training. Okay, that being said, let's get started. So this is a bit of an outline of part of this training. It continues on the next slide. So we'll start with an overview. And then we talk a little bit about the process model, so the application model, and the language bindings. And then we start with point-to-point communication. And interesting, it's a good way to get started, but it's something that perhaps in practice is not always that useful because typically you want actually collective communication. Then we need to talk about non-blocking communication because one of the issues with parallel programming, one of the potential issues, is deadlock. And of course, that's something you don't want because that's wasting resources big time. Then for those of you who are using Fortran, there are some annoying catches here. So this is one of the few exceptions where I tell people who program Fortran, okay, bad luck for you, because your life is even more complicated in this case than the life of C and C++ programmers. That is really exceptional, but yeah, that's unfortunately a reality. So there will be a brief, it's not that, I think it's 7 slides or something, about specific things that you really, really need to take into account as a Fortran programmer. Then we go on with collective communication, which is a very important topic because typically that's the building blocks for the majority of your applications, essentially. Then a little bit about error handling. That will be shortish. And that is probably going to be it for today. Maybe including error handling, maybe not. Maybe a little bit about groups, we'll see where we get. But at any rate, at some point you need to kind of structure your communication, and that's where groups and communicators come in. So that's also an important topic, which we'll cover in some detail. Then we'll also talk about virtual topologies, which make your life a lot easier in certain circumstances, of course. Then there is one-sided communication. That's if you're used to classic MPI, that's an interesting concept, which may or may not be useful depending on your application. And then there is shared memory, one-sided communication. So essentially, you have a few options if you want to do shared memory programming. The obvious choice is OpenMP. Some of you attended last week's training on OpenMP. So that's one option, and it's likely the most common one still. But there is an alternative within MPI. So you can do hybrid programming, so shared and distributed, in the context of MPI only. That's an option. So yeah, it's worth considering. And then there is derived data types, which is quite important in order to give structure to your messages and essentially messages into concepts that actually make sense in terms of your application. And that's also a pretty extensive chapter. And then there is, of course, file I/O, which is in terms of parallel programming, unfortunately rather important. And that builds on top of derived types. Might sound weird, but yeah, that's the way MPI I/O works. Then a little bit about MPI and threads. So essentially that would be bridging your MPI application with multi-threaded programming using, for instance, OpenMP, and in practice, typically OpenMP. I don't think many people do role threads in scientific programming. There are reasons to do that, but not in this context, most likely. Then there are a few things which are kind of interesting. Probe can be useful. So that is something that we will also check. So that's actually looking at messages and see how they, what they actually contain. Persistent requests, cancel, and so on. Then process creation and management. Yeah, you can dynamically create MPI processes. Whether that makes sense in the context of scientific computing is a somewhat different discussion. So yeah, okay. We'll talk about it anyway, because maybe it can be interesting. Then a mixed bag of other MPI features. And then, of course, very important chapter is best practices. How do we kind of write MPI well? Okay, there are a lot of acknowledgements. I'm going to let you read them. I'm not going to read them myself. They're rules, so not mine. So let's not go there. And then quite some information about MPI. I'd say that the main source of information about MPI is actually the specification. And back in the days, you could buy them as, well, slotted trees. And I actually have a copy of those old ones. Basically, it's a book like this. So it's a really, really extensive specification for a number of reasons. I think there is a slide about it, otherwise I'll show you. But nowadays, of course, in these modern times, the specification is available as a PDF file. So you can download that, you can use it. And you might say, okay, specifications, well, who cares? Well, on the one hand, specifications are important because they tell you how to use things correctly. So that makes sense. You can say, okay, that's why I'm here. Okay, great. But still, it makes good reading. So in fact, I'm really admiring the authors of the MPI specification because it's a really well-written document that is kind of nice to read. And for specifications, that, in my opinion, is at least an achievement, because typically specifications are very formal and you really have to, okay, don't start reading it in the evening because you will fall asleep. So basically, this is different. This is really well written. And also there are some details like, it's a specification. So of course, it doesn't say how things are implemented, only what they should do. But there are also hints to implementers. And you might say, okay, I'm not going to write my own MPI implementation. I'm not going to write my own MPI library, which is true. But these hints give you interesting insights into design decisions that might have been made in your MPI library. So that is also interesting reading, because they give hints at how to optimize things. And indeed, that's most likely how your friendly MPI developer has actually done that. Okay, then there are a number of old books 2014 is reasonably okay. And let's see whether I want to mention something in particular. No, not really. Okay, but as you can see, there are not exactly many really recent books, as in like none. So basically, that is not such a big deal because 2014 is actually good enough in the sense that that means that it covers MPI 3.1, specification 3.1, which is what you will mostly be using. So in that respect, it's still worth getting such a book. One of them which I like isn't there, but okay, let's not go there. Okay, so that being said, let's first have a bit of an overview about what MPI is and so on. So what's the idea? You have a sequential programming paradigm. So essentially you've got the data, and that of course resides in memory somewhere. And then you have your program, and that runs on something, a processor, let's call it a processor. Of course, in practice nowadays, it's a single core, typically if you have a sequential program, but let's call it a processor to keep things general. Okay, so you know how that works. It's kind of easy. Now, how does it work if you use MPI? Well, you have many of those individual processes. Each has its own data. Each runs its own subprogram. Okay? But they communicate. They can talk to one another. They can exchange messages. And they do that via some network. That's basically the idea. Okay, so this is an analogy which you can use if you want. So basically, we've got a house, and there is, or there are, rather, a number of electricians who are installing the electric cabling. Okay, so how can you parallelize that? Well, of course, each of those technicians can work on a floor and complete the floor, and then they connect and so on. So basically, I think you will agree that this is something that can happen in parallel. Okay, so an MPI subprogram is basically the work which one electrician is going to do. So it's the work which gets done on on one of these floors. Okay, so basically, the thing that's doing the work here is the technician. So that would be your processor, essentially. And then the data is the electric installation and the communication. So basically, a number of things are important if you have multiple technicians, because essentially, yeah, at the end of the day, they should all end up here, so that the electricity network is actually interconnected. And they might also want to communicate while they're testing the network, in the sense that, okay, if you switch the master switch on and someone is still installing something, then you get well, unpleasantness, like people getting fried and so on. So you can see that some communication is needed in order to coordinate the work. Okay, so let's talk a little bit. This is actually a similar slide as was shown in the OpenMP training, but let's talk a little bit about parallel programming in general. So one of the paradigms of programming is shared memory. So the whole thing happens on a single computer, on a single compute node, let's say. And of course, that's something that you can also do simply on your laptop or on your desktop system, no problem. So essentially, there are a number of, this is your CPU. So essentially, it has a number of cores. And each of those cores can process a process or a thread independently of the other cores. That's essentially the idea. However, they share a memory interface to memory banks. These are the RAM chips which you typically have in your DDR RAM, etc., which you typically have in your laptop or in your compute node. Okay, and each of those cores can actually, through the memory interface, connect to that memory, get data to that memory, store data in that memory. That's essentially the idea. And this is a CPU. So in a computer, a CPU resides in a socket. Okay, just lots of connections. And basically, you can do shared memory programming there. And then, of course, parallel execution, for instance, you've got a large array, and the first core is going to process the first 1,000 elements of that. The second core can process the next 1,000, etc., etc. At least in the assumption that there are no dependencies between processing either of those array elements. Okay, that's sort of easy. Then, in a typical compute node, the situation gets a little more complicated, and the complication arises from the fact that you no longer have a single socket, but you have multiple sockets. And typically in compute nodes, there will be 2 sockets, so you actually have got 2 CPUs. Each CPU has its cores, etc., etc., the usual mantra. Why is that important? Because if you log into a compute node and you ask for the number of cores, actually what you will see, what the operating system will tell you, is that you have, as a number of cores, the sum of the cores on one CPU and on the other CPU. So basically from the operating system point of view and from you as a user point of view, essentially it's as if you have one large CPU, although they're actually 2. Okay. So in some situations, you've got 4 sockets rather than 2, but yeah, that's typically very expensive. So one of the applications of such nodes in HPC would be to have really, really large amounts of memory. Although nowadays, typically, even with 2 sockets, it's more than good enough. So anyway, but that would be one application. Okay, so if from the perspective of the user, if from the perspective of the operating system, it seems as if you have one large CPU rather than 2 separate CPUs, then what's the point? Well, the point is basically that it complicates matters a little bit, because under the hood, if you look at the hardware, there is of course extra hardware required in order to make sure that these sockets, these CPUs, can actually exchange information, that they can get data from one CPU to the other. And for that, you need a hypertransport, which is here. Okay. Now, remember, each socket itself has its memory bank attached to it, one or more memory banks attached to it. So basically, that means that if, let's say, the CPU on socket 2 needs some data which is in the memory attached to socket 0, then that data needs to pass through the hypertransport. Okay, so basically that means that you have an extra communication channel in between, and that is going to determine the bandwidth for the data that moves from one CPU, from one socket to the other socket. That's essentially the idea. So in HPC computing, you kind of need to take that into account, because it introduces some extra latency and it reduces your bandwidth a little bit with respect to just using the memory interface of the socket itself. That's of the order of 10%, so it's not something huge, but yeah, you have to start thinking about that at least. Okay. So essentially, here if you have a single socket, you have uniform memory access. So essentially, each core gets to the data equally fast, which is sort of true, except if you use an AMD, then it's not true, because there are preferred memory paths in an AMD, and also you can, but probably, yeah, we had that at some time. You can even define multiple UMA domains on a single CPU as well. Whether that was a good idea, has never been really clear. But okay, you can do that if you want. It makes life again a little more complicated, but okay. There are pros and cons, but it's not really clear what's the best unless you do extensive testing. Or if you have a single workload, if you run an application all the time, then it makes a lot of sense to look into that. Otherwise, you don't really care. Okay, once you get multiple domains, then you have CC NUMA. So essentially cache coherent, that's what the CC is for. NUMA, non-uniform memory access. So the non-uniform, of course, comes from the fact that you have got this hypertransport in the way, or your memory mesh in a AMD CPU. Okay, but there is still CC there, so there is still a cache coherence. So essentially you can be sure that at given points, and of course that's a rather long discussion, what those points are, etc., etc. But mostly from a practical point of view, you don't have to care. You can assume that everyone has a coherent view on the data which is in the memory. That's the idea. So essentially there are protocols in order to ensure that, and that's what this cache coherent means. Okay. So nitty-gritty detail in a way, but yeah, it's important that you are aware that that might be an issue. Okay, so all of this is shared memory programming. You can do that with OpenMP, you can do that with Cocos, you can do that with TBB, you can do that with many things. You can even do that just with with MPI. Okay, but things get, of course, more interesting when we've got distributed memory. So when we want to run an application on multiple compute nodes, then things get interesting. And then the number of choices decreases. And I would say that the de facto standard in that case is to use MPI. Of course, now we have non-uniform memory access. Note there's no CC anymore. Basically, if a node requires some data that is in the memory of another node, it will have to ask for it. And of course, you can already guess that that will take more time than getting something from memory on the same node, because then you are restricted by the bandwidth of your network. And that is typically lower than your memory bandwidth internally within the node. So that really makes the N in non-uniform pretty important in the context of MPI programming. Okay. Now, that would be MPI, and as I already mentioned, if I want to do shared memory programming, I can actually also do that with MPI. I don't even need to do explicit shared memory programming. I can simply run one MPI process per core, and I also get my parallelism. That's not shared memory then, but okay. I can run my MPI application on a single node if I want to. Okay. So basically, what is the programming paradigm here? The programming paradigm is exchanging messages, sending messages around, basically to your processes. And essentially, what you have is that if you have such an MPI program that's written in some conventional sequential programming language, that programming language need not have any provisions for doing parallel programming. It's just an ordinary language, C, C++, Fortran, Python, typically those are your languages in which you can kind of conveniently do MPI. So that's basically the idea. So essentially each of these sub-programs you can view as a conventional program, just a MPI, just a Fortran or whatever program. And typically, but not always, we'll see how to differentiate. So basically, normally the same code, the same program is running for each process. So they're all kind of doing the same thing, Of course, that would be a little bit boring and wasting taxpayers' money. So what they typically do is do the same stuff on different data. So that's what the SPMD stands for, single process, multiple data. That need not be the case. You can run different codes on one node in one process than in another. Really different codes. We'll see on the one hand when that makes sense and also how to do it, but that's for tomorrow. But yeah, you can do MPMD as well, so local program, multiple data. That is also an option. MPI doesn't restrict you to SPMD, but your typical MPI program is SPMD. Let's put it that way. Okay, now in each sub-process, given that it's essentially the same code, all the variables are going to have the same name. If you have a temperature in one sub-process and the variable name of that is uppercase T, for instance, then that will be the same in each sub-process. But they will have different locations in the sense that they will reside in memory in different places on the same node if you have multiple processes, and of course in the memory of different nodes if your application is running on multiple nodes. And of course they will all have their own values, which may or may not be different. But the idea is the data is private to a process. So there is no, in typical MPI, there is no shared data. That does not exist. Everyone has its own private memory. That's not really true anymore if you like, but it's an opt-in. If you like, you can share memory. That's not a problem. We'll see how to do that tomorrow. But your typical classic school, I'm not going to say old school because that would sound derogative, and that's certainly not my intention here. Your typical classic setup is that everything's private. So basically a process has its own data and works on its own data only. That's it. Okay. So basically we need to somehow synchronize things to exchange data, exchange state. So how do we do that? Well, just by passing messages. And that's why you need a communication network. That communication network can just be essentially your CPU, because cores can talk to one another. So essentially via shared memory. But it's also possible, of course, to do that via another network, such as Ethernet or preferably something a bit more performant. Okay, so this is very different from OpenMP. So for those of you who attended the OpenMP training, what you learned about OpenMP, just shut it away for a moment and just approach this as something fresh, because this is a different approach to things. Okay. So how do we distribute data? How do we distribute work? Well, essentially, what we have is that each process has an identifier. And that identifier ranges from 0 up to the number of processes minus 1. So essentially that means that each process can sort of identify itself. It can get its identifier, and that identifier can be used, for instance, to distinguish work. For instance, I could use that in order to compute the indices of a distributed array I'm working on. So this is basically your identification thing. And typically, these processes are started by a helper program, typically MPI run, or sometimes on Slurm clusters you can use srun directly in order to start an MPI application. So basically, once you start your application, again, classic school, that's the number of processes you're going to get, and those exist during the lifetime of your application. You can do that differently. We'll see that tomorrow. But I don't think there are many of such applications around. I've never heard of one. And I'll also explain you tomorrow why it's not necessarily very useful to dynamically create new processes and make them disappear and so on. That does not necessarily make much sense in our context. Okay, so all decisions are based on the rank. So basically, there is the data of the process with rank 1, data of process with rank 2, and so on. So basically, that is determined, again, by the rank. That's the idea. We will make that a little bit less abstract quite soon, so don't worry too much about it. Okay, so SPMD, as I already said, single program, multiple data. So essentially, that means each process runs the same code. Of course, different things may happen based on the rank, but okay, apart from that, they run the same thing. But of course, you can, as I already said, do MPMD, so multiple program, multiple data. And basically, yeah, I think this is no longer true, that some vendors are restricted to SPMD. As far as I know, everyone does NPMD in some format. And anyway, it's very easy to simulate. So in that respect, no one cares. Okay, so here would be an example of multiple program, multiple data. So I can make a decision based on the rank. And actually, I can also do that differently, but again, it's more. This is a very classic way of simulating NPMD. Essentially, you can do that a bit more sophisticated nowadays, but okay. But let me explain the example first, or the motivation for why you might want to do NPMD. So what you want is a weather model, and you have two codes written by yourself or not, whatever, no one cares. But basically, you have a code that does the simulation of the atmosphere, and you also have a code that simulates the ocean. And of course, I don't need to tell you that what happens in the atmosphere is going to influence what happens in the ocean and vice versa. But we've got these two distinct models. It's distinct physics, so yeah, it makes sense to have two different models for that. And what I want is that, of course, those models get coupled, so that in my complete simulation, the effects of the atmosphere on the ocean are taken into account, and the effects of the ocean on the atmosphere as well, by temperature exchange and whatnot. Okay, so actually I want a number of processes to do the ocean simulation, and I want another number of processes to do weather simulation, and I want to couple the two at some point. So this would be kind of skeleton code for C, skeleton code for Fortran, and skeleton code for Python. Okay. So you can do that in several ways, and one way to do that is indeed use process groups. Then you create a group that contains the processes involved in the ocean, another group which contains the processes involved in the weather, and you would define a communicator within each of them, and one which bridges them, to put it that way. Okay, so let's do an example. And yeah, this is a training that is intended for people who do C, Fortran, and Python. So basically that means that some examples will be in C, others will be in Fortran, some will be in Python, but typically you will understand what's going on. But before I continue, I would actually like to do a brief poll and see who is doing what with respect to programming languages. Okay. The order is just alphabetic. No, it's not, but it happens to be that way. Okay. So basically in the room, what are you supposed to? That is what I'm doing. Okay, lots of Fortran. What are you doing? Fortran? So everyone here is using Fortran. Okay, but skip the C part. No, we're not. Okay, so yeah, as usual, the mix between Fortran and C++, and there is one person who does Python. So we will do all three anyway. Wait, you said you asked for 4 options, and now you're saying 3. Yeah, basically the C people are somewhat out of luck. You will have to use C in order to do MPI. You can mix that into your C++ program, that's not the point, but basically the standard is for C and Fortran only. So there has been, with the emphasis on the past tense, there has been in the standard an interface for C++, but that has been deprecated for quite a while. So that's something which we're not going to discuss, and which I would really, really strongly discourage you to use, because that's going to be a very bad idea. Okay, I can stop the poll, and let me switch back to the chat. Yes, one thing I forgot to mention during the introduction. If there are any questions, please ask. The more interactive this is, the nicer it is for me, and maybe the most informative it is for you. So feel free to ask questions. For the people online, feel free to just type them in the chat. If it's too complicated, I can ask you to activate your microphone and just ask your question verbally. But basically, please ask questions at any point. I mean, I can only encourage that quite a lot. Okay, first example. I'm very sorry for the room. This is C, but you'll understand what's going on anyway. It's not that hard. So of course, we need the definitions of all the functions we're going to use. So basically, we need to include a header file. That's the usual thing in C. That gives us all the declarations of the functions we are using. Okay, then we've got our main function. That would be the equivalent of program in Fortran, sort of. So basically, that's the function that's always going to be executed. Okay. There are 2 things which we definitely need to do in any MPI application, and that is MPI init and MPI finalize. And this has to be done before any other work. Why? The specification says so. It's in the MPI specification. So you should just do that. Okay. So basically, as you can see, there is an MPI init here, and there's an MPI finalize here. So basically, what you can do typically doesn't make much sense at this point, but what you typically do is you pass in the command line arguments into MPI init. That's for C, C++. There are very little practical implications of that nowadays, so typically I don't bother doing that, but you can. Okay, we need some variables, of course, and in, let's say, C89, you have to declare your variables up front. You can't do it in your code, so that's a little bit like Fortran. Nowadays, of course, there are probably no compilers left that don't support C99, but okay. So basically, you can actually declare your variables where you like. It doesn't matter in C anymore. But okay, let's assume that we declare them up front. So this I can do before MPI init. That's not a problem. Declaring variables, no one cares about. Okay. Then you notice 2 function calls. One is MPI com rank, and the other is MPI com size. Okay. And for the Fortran people, basically this ampersand here means this is a call by reference. So I'm going to modify the value in my rank and in my size. Oh, sorry, in num process. Okay, so this is fairly straightforward. I think that the semantics is clear. I just want for each process it to have two things. On the one hand, its rank, and on the other, the total number of processes. Okay, so there is a somewhat mysterious first argument here, MPI conworld, and that is basically your communicator. So you can view that as sort of a handle on your communication network, abstract. But okay, never mind. All right. Then we can do something. So for instance, if I'm the process with rank 0, I do some printing here. So basically I'm printing the number of elements in something something. So basically I'm actually going to ask for that on the command line. Please don't do that. That's not a good idea, but okay. This is just for demonstration purposes. And then I'm doing the first communication. So up to this point, I've not been communicating yet. The MPI init is just setting up stuff, but once that's done, I can start communicating. And one of the things I can do is a broadcast. So somehow, in this case, reading from standard input, process 0 has obtained a value, and that value is n. Okay, that has meanwhile also been declared here somewhere. There it is. So each process has this variable n. Okay, now process 0 is going to initialize it somehow, in this case reading standard input. Okay, but we want all the processes to have this value n. So we need to send a message with that value to each and every process. Okay, an easy way to do that is using a broadcast. So bcast stands for broadcast. And as you can guess, broadcasting just means, okay, I'm process 0, you're process 1, 2, 3, 4, okay, me saying n is equal to 10 is broadcast, because you're hearing that, and now in your head, n will also have the value 10. Okay, so that's essentially what happens here. Let's not go into the details of this function call because it's rather involved. The 0 here essentially means this is the process that is going to actually define the value. It's going to do the broadcast, so that would be me saying n is equal to 10 in this case. Okay, and again, note this MPI conworld, so the handle on your communication network. Okay. And then we do some computation based on the rank and on this value of n. Okay. And we print that. Okay. And again, if my rank isn't 0, I'm going to do something. Now isn't 0. So all of you have now done a computation based on your rank and on n. And you're going to send that somewhere. So MPI send means send a message. Okay. That's going to be the result, as you can see. Forget about this for a second. And it's going to be sent to, this is destination. It's going to be sent to process 0. Okay. Again, some details which we're going to skip, and MPI conworld. Okay. So all of you know what to do. Now I, as process 0, need to know what to do. You are sending me a message. I've got to receive all those messages. Okay. So the else is process 0, and I'm going to define local variable rank. Doesn't matter. Okay. So I'm going to loop over all the ranks, not including mine. Hence, this loop starts at 1. And I'm going to do an MPI receive for a message that's coming from that rank. See, here's the rank. So that's whom I'm expecting to send the message to me. That's basically the idea here. And I want to store the message which is being sent in the variable result. Okay. And then I'm going to print and I'm going to say, okay, process whatever, send me whatever value. Okay, so then we're done. Then we're in MPI finalize. So important rule, let me repeat it. No work before MPI init, no work after MPI finalize. Those are always the first and the last things you do. Everyone needs to call MPI init. Everyone needs to call MPI finalize. Must be. Specification says so. It's the law. Okay. Yeah, sure.
About the precast.
Yes.
Well, imagine now a bigger code. That means that the processes can be at different places in the code. So depending on the application, sometimes we want to wait them at the one part of the code before doing the precast, or how is it typically used?
Okay, so it's an interesting question. How is B typically used if you have, let's say, a large application and you are not sure? Well, some processes are a bit faster than other processes. So you've got a bit of load imbalance. Okay, your MPI broadcast is going to synchronize. So basically, certainly the processes that are waiting for the incoming message, they are going to have to wait there until the source has actually sent this message. So it's pretty clear that it will be synchronizing, synchronizing on the sending process. Because before process 0 in this case has sent the message with the broadcast, the others can't receive it with the broadcast. That's not possible. So you get synchronization here.
So it's waiting, the other process will wait.
They will be waiting for process 0. Yeah, exactly. Yeah. In this case, yes. There are ways around that, but with non-blocking communication, but we'll get there later on. But yes, MPI processes, MPI calls can have the effect that things synchronize, so that you indeed processes start waiting for other processes. That is indeed a possibility and a danger, because of course that leads to load imbalance. That means that some of your processes are just sitting there waiting for other processes which are slower to finish and communication to happen. So that is indeed a very important consideration when you're writing MPI applications. Do I have a load balance? Do I have load balance issues? If so, I need to take that into account if I want efficient code. So that's indeed important. But we'll get to that in much more detail later, no worries. Also in best practices and so on, we'll address this in some detail as well. But very good question, indeed. Okay. So now actually we can do the same thing for other programming languages. And of course, I would say, okay, try this in your own programming language. Concretely speaking, do this in Fortran. So of course you need MPI to be installed. Typically your friendly HPC cluster will have that. I'm not going to use the cluster, I think. Am I? It's more convenient to do it locally and so on and so on. Okay, let me not do that. But basically, let's do this application quickly but we can do the whole thing. What we can also do is, because are we not supposed to do the whole thing, or do we just do an MPI? And let's see, tasks, blah, blah, blah. Okay. Okay, so that's the one. Yeah, okay. So that's basically the code. So rather than just copy pasting the code, let's just write it ourselves, at least in part. So the C example you've seen. So let's do the Fortran example. Let me call it very originally example 1, F90. Okay, so we've got the usual program example, 01. Okay, and program example 01. Implicit none. Use MPI F08. We'll discuss this later on, but this is basically the equivalent of our include in C. So I'm sort of doing the exact same thing here. We need an integer to store the rank, so my rank, and number of processes, and we also needed an n, and no, we don't need that for now. Then we needed a double precision result. I'm just going to use real here. I don't care whether it's double precision or not. Yeah, I do care. So let's also include, so let's also use ISO Fortran env. And yeah, I'm going to split them up, then it's a little clearer. So use, okay, and I want not real 32, I actually want to use real 64. Okay, and then this is going to be a real 64. I want to do that because one of the things that I need to do in order to do the send is specify the type of the variable, which I'm going to send the value of. So basically I need to make sure that I have the right type, so it's better to do it explicitly. Okay, so MPI init. Okay, call MPI finalize. Always a good idea to just start with that. And then we start doing the calls. So basically I can do the rank, the size. Okay. Now if my rank is 0, then I'm going to determine n. I'm going to do something pretty stupid. I could do this read thing, but personally I don't like it that much. So I'm just going to say that n is equal to 100, whatever. Okay, I can determine n in any way. Let's not go with reading from command line, from standard input and so on. It's not going to add anything. Okay, so then we have the call to broadcast. Okay, so after that call, and notice everyone has to call the MPI broadcast. That's also very important. Now they have the values. So basically now we can compute result as it was something like n times my rank, I think, something like that. I don't quite recall. And then let's see, I have to cheat a little bit because I don't remember what was computed exactly. 1 times, yeah, okay, just to convert it to a real. Yeah, okay, whatever. Okay, there are other ways to do that, but let's not go there. Okay, so again, if my rank is this, then I'm going to print it. Okay. For my rank. All right. Now, if my rank is not equal to 0, then I'm not going to print it, I'm going to send it. So again, call MPI send. I send the result over. And in fact, I could use, I'm not so sure, this is not standard, so I should actually use double precision here. And I think I have to use the full form. We'll see what the compiler says. I'm not 100% sure here. Okay, so that's one thing. Then we have the else. So if my rank is not different from 0, okay, so now I know that rank is 0. So this is again rank 0. And then indeed, what I'm going to do is I'm going to, but not from my rank, because that's a really stupid idea. Let's add an additional variable here, rank. And that's when you get when you use generative AI to do your stuff. It gets things wrong. Okay, so I'm going to read from this guy with some details which we're going to ignore. And okay, this is going to be printed, and we are done if I remove that nonsense here. Okay. So in theory, this should compile if I didn't do too many stupid things. So let's see whether it actually did. G4, no, not G4, MPI F90. And what have we got? Example. It compiles. Wild. And a.out, sorry, not a.out, MPI run. NP is 4, for instance, a.out. So this is my launcher. So basically I'm saying, okay, launch 4 processes. And that's what the NP4 is for. And the application which should be run is a.out. And then indeed, I get some results, and they seem quite reasonable given what I wanted. Oh, wait, I forgot one thing. Okay, actually, this is what I want. I want to show where the thing comes from. And of course, I forgot to rename that variable. That was still generated code. So, okay, let's recompile and rerun. Okay. And as you can see, I get the results where I expect them from. And I can do that for more. Oh, that's what's going on. Ah, okay, yeah, it's I shouldn't go up to, this is the maximum I can do on my machine without it starting to complain. And it's interesting, so it actually knows about, it uses the actual course rather than the hyperthreads. Oh, that's interesting. Okay. So basically, as you can see, again, the result is correct. Okay, so yeah, it's quite easy to do. And of course, there are many things which I just glossed over. So we will go into more details in a minute. So one of the things that I already want to draw your attention to, so you can see that if I try to run it with 10 processes, MPI run starts complaining. It says, well, okay, that's nice, but actually you've got 8 cores in this machine, and you're asking me to run 10 processes. That is probably not what you want to do. I can override that. I can say, okay, I don't care what you think about it. Please do what I ask. But it's not a good idea in general. Why? Because, of course, a process running on its own core means that it gets all the processing it can get. If you start having more processes than cores, that means that some processes are sharing a core, and that's of course going to slow you down. because then that means that the one process is going to be interrupted in order to run a second process, which is going to be interrupted in order to run the first process again, etc., etc. So basically, that would generate quite a lot of overhead, and in general, that's not what you want to happen. So that's why MPI run simply says, well, okay, are you sure that what you're asking me to do is a good idea? If you're sure, please specify as such. I won't do it by default. So this, of course, is specific to MPI implementations. So it might be that you've got an MPI implementation that doesn't do that. But okay, this one does. All right, so that was the Fortran thing. Let's so essentially, if we look at access, basically data that is owned by a process cannot be accessed by another process. So essentially, that is basically the only way to get information is to use the message passing system, and you can compare that a little bit to a mailbox, to a phone system, to fax machines, etc., etc. And we will use all these analogies later on in order to kind of explain some details. So essentially, what you need to do in order to run an MPI application is to run it, to link it to an MPI library. And as you see, I did not compile with G-Fortran. I did compile with MPI F90. This is a wrapper, and that will, under the hood, happily call G-Fortran, no problem. But it will automatically set the link options, which I require in order to link with an MPI application. So it will specify some dash capital L for the link path to the MPI implementation of the library, and also a dash capital I in order to get the header files, and dash lowercase l in order to link in the specific libraries, and so on and so on. So the MPI wrapper, either MPI F90 or MPI CC, or MPI CPP, is going to do that for you, no problem. Okay, so then, of course, the total program must be launched with an MPI startup tool, which is typically MPI run. The startup tool is not covered by the MPI specification, so that is implementation specific. That's why I'm mentioning that indeed for the for the MPI library I'm using, which is most likely OpenMPI. Yeah, that will be OpenMPI. The MPI run is going to warn me if I try to launch more processes than I actually have cores available. Okay. So messages. We already have seen a point-to-point communication. So there is one process that sends a message, the other that receives it. And that was the oldest form of communication in MPI and is still, in a number of circumstances, useful. So we have a sending process and we have a receiving process. There is a source location, there is a destination location. There is a source data type, there is a destination data type, and there is a source data size and a destination buffer size. So essentially, all of these things are in either the sending or in the receiving process. So, but we will go into the details later on. Okay, so addressing, you've already guessed how that works. It's quite simple, it's based on the rank of a process. If I want to send a message to a certain process, I just specify its rank. If I want to receive a message from a certain process, I just specify its rank. Easy. So that's what it's based on. So compare that to a phone number, compare that to a fax number, etc., etc. Okay, so one very important rule that's in the specification, and there's no one that forces you to do that, so it's something that you have to do, but you don't have much help there, is basically you have to make sure that every message that gets sent also gets received. So it's not allowed to send a message and no one is getting that message, no one is receiving it. This you shouldn't do. And that is in the specification. It's very clearly stated, but it's not enforced. And I'll explain you why it's not enforced. There is a big difference here between OpenMP on the one hand and MPI on the other hand. So in OpenMP, that is the compiler's job. The compiler is going to generate code for you. So the compiler can also do various verifications to see if your OpenMP directives make sense or not. So from the compiler's perspective, OpenMP is transparent. Your OpenMP code is transparent. Okay. What is MPI? MPI is purely a library. So basically the compiler has no access to the implementation of MPI things. The compiler doesn't care about function calls as long as the functions which you're calling exist. It's happy. The linker will link them in, but there is no semantics there. So the compiler is not going to help you. The compiler cannot help you. There's no way it can do that. So that's an important distinction between OpenMP and MPI. If your if your OpenMP application compiles, it at least makes some level of sense, because otherwise your compiler would say, can't do that. If your MPI application compiles, it can still be quite incorrect. For instance, if I don't do any receives here, in this example, it is going to compile, it's going to link, and it's going to be very incorrect. And no one can tell me, except me noticing that things go badly wrong at some point, hopefully. But okay. So we've seen an example with the send-receive of what's called point-to-point communication. So basically, process A communicates with process B. That's the idea. That's point-to-point, or peer-to-peer. There are several terms for that. Okay, it's indeed the simplest form of message passing. It's very similar to me phoning someone. It's a one-to-one. Okay. Basically, one process sends a message to another process, I already told you, and there are some types of point-to-point communication, and we will go into details later on. So there is synchronous send, and this you can sort of compare to a fax machine. So basically, we've got two fax machines. Okay, so I'm going to send a message. The message is being transmitted, and I get a confirmation that that message was received. That's what the fax machine does. It gives you a beep when the receiving fax machine has actually successfully dealt with your fax. So that's essentially the idea. So basically, you get the information that the message is received. That's synchronous communication. Okay. Then you can also do buffered or asynchronous sends. And that is similar to what you do with the classic mail system. So basically, you write your letter, you drop it into the mailbox. Okay. Magic happens. Postman delivers it to the mailbox of the receiver, and the receiver reads the message. But the sender has no clue whether or not his message has been delivered, whether it has been read or whatever. So this is asynchronous send or buffered send. And we have both of them. Then there is another important concept, and that's whether communication is blocking or not. So what does that mean? Well, essentially, operations are sending and receiving. Up to this point, we know that. And then there are some operations that may block until another process acts. So for instance, a synchronous sense operation is going to block until the receive is posted. So basically, the synchronous send will wait until it got confirmation that the receive is in progress. Okay. The receive operation will block until the message has been sent. Yeah, obviously, I mean, if you wait for something, if you want to receive something and it's not there, okay, what are you going to do? So that's blocking operations, and that has to do with the completion of an operation. When is it done? So you can have blocking, you can have non-blocking. So blocking subroutines will only return when the operation has completed. Okay, so non-blocking operation. In fact, your fax again is an example of a non-blocking operation. What do I mean by that? Well, I put the message in the fax machine, in the sending fax machine, and I go away and do something else. For instance, I go to the coffee machine, I take a cup of coffee, and then after a while, I'm going to check whether my fax has been received. So this send operation would be a synchronous non-blocking operation. I don't wait for the confirmation. It's a synchronous operation, so I get confirmation. I don't wait for it. I go to the coffee machine, do something else, and then after a while, I can check whether it's there. So this is non-blocking. Non-blocking synchronous. Okay, so basically, all non-blocking procedures must have at some point a wait operation or a test operation. We'll see that in more detail later. So, of course, if you have a non-blocking operation immediately followed by a wait, okay. So for the people online, there unfortunately seems to be a fire drill, which means that I will have to evacuate the room. I hope we will resume in something like a quarter of an hour. Usually this kind of thing takes that amount of time. I do apologize, but yeah, this can't be helped. I'm legally obliged to do that, so it might be real, who knows. Okay, so basically usual operation, leave everything here. I will not move, no problem. So you can leave your just leave the building fire door. Okay, fire drill over. As soon as everyone's back, we resume. Right. So I hope the people online had a chance to get something to drink meanwhile. Okay, so let's continue. Let me show the this thing, and okay, there are some comments. Is there any difference between MPI and MPI? Sorry, MPI run and MPI exec? Yeah, the format of the command line options is a little bit different. Apart from that, I would have to check the documentation. I typically use MPI run, to be honest. So, but be aware that if you have an MPI run that is defined by, say, OpenMPI, and you compare that to the one for Intel MPI, for instance, they will be different. So command line arguments will be different and so on. So that's something to keep in mind. MPI run is not covered by the MPI specification. So any vendor, any developer of an MPI library does exactly what that person wants. No one says what should happen there, except that at the end of the day, you should have the specified number of processes and all the communication stuff set up. That's the only thing that is specified. Okay, so what's the difference between send and broadcast? Another interesting question. So basically, a broadcast is, let me just give an example. If I tell you out loud and everyone hears me saying that n is equal to 10, that's a broadcast, basically. The alarm sound is a broadcast, so everyone hears it. While send and receive is specific between two processes. So that would be as if I sent you an email with a value of n. I put no one in carbon copy, I put no one in CC, so I communicate the value directly and only to you. So that is send and receive. Send is me hitting the send button, you is opening the message. That's the receive. Okay, so send receive is point to point, process to process. Broadcast is collective. Everyone is going to hear what I say. So that's the difference between send receive and broadcast. Okay, but don't worry, I'll come back to the details later on. So non-blocking. So essentially, if you have a non-blocking routine, so it starts something and then returns, and you immediately in your source code follow that by a wait, yeah, then you have something that is blocking because the wait is going to be blocking. So that typically doesn't make much sense. You want non-blocking operations for a number of reasons. One is to potentially avoid deadlocks, that's one thing, but also to do stuff while something else is running. So for instance, the example which I gave you in real world, I send the fax, I go to the coffee machine. Once I have my coffee, I return to the fax machine and I see the confirmation. So that would be a real world example. in terms of computations and so on, what you would do is you would send a message, but transferring that message takes time. So meanwhile, while you're waiting for the message to be delivered, you can do some computations. And then once you've done those computations, you can check whether the message was safely delivered or not. So that would be an example of why you would want to use non-blocking communication as well. So basically, to put it in technical terms, to overlap communication and computation. I do computation while the communication is in progress. And I can't speed that up anyway because that is bound by the latency of my network and the bandwidth of my network. So I have to wait anyway. So while I'm waiting, I can just as well do some useful work. That's essentially the idea here. Okay. So, example. So one of the things that you often need to do is, and that's, for instance, solving partial differential equations numerically and so on. So that is stencil computations. So essentially you have a two-dimensional domain in this case, and you can generalize that if you want to 3 dimensions, or you can also do that in 1 dimension. As such, it doesn't really matter. But the two-dimensional picture makes for nicer graphics. So basically, what you do, in fact, is you have time steps. And each next time step is determined by the current value and the current neighboring values. So you've got a stencil. In this case, you look at the cell itself, its upper neighbor, its lower neighbor, its left neighbor, and its right neighbor. And the values of those are going to determine the value of the center position at the next time step. That's essentially the idea. Okay, so typically that's pretty straightforward code. The only thing you've got to do is to have a nested for loop over each of your indices to compute the next time step, and then of course you have a for loop over all your time steps. Okay, so that's easy to parallelize, because what I can do is just distribute all the data over a number of processes. Okay, so I could do it this way. The total domain is the same size, but now I've cut it up into 4 parts. So each process is now responsible for updating its own part of that memory, of that data structure. Okay, but of course, you immediately notice that there is an issue now. Because how am I going to compute the values on the edge? Because this process here, let's say the upper right one, doesn't have the information about the state of the system in this point. Okay, so it needs that information. So basically that means that it will need to get that from its neighbor, so the upper left process. It will need to get that value. And of course vice versa, because this guy here, so upper left, also needs information from upper right. And of course the same in all directions. And then of course if you have cyclic boundary conditions, things get even more interesting. So essentially what we need to do is we need to exchange information. And we need to do that before we can do a computation. So before we can compute a new time step, we need to exchange information. We need to exchange these boundaries. All the values which are here need to be communicated to this guy. All the values which are here need to communicate it to that guy. Same for here, there, etc., etc. And that's typically called a halo, because we need a halo around our specific domain. So the halo in this case would be such a thing here. So basically, all the values which are just outside of the domain. That's essentially the idea. Okay, so you would have to do that in each direction. And of course, you don't want to send all those values one by one. You want to do a send of the entire sub-array, let's put it that way. So basically what I want is that one message is sent that contains all this data, and it's sent here, and vice versa. All the data here on the last row needs to get sent in one message to its lower neighbor. So that's important for performance, and that's something that we will see how to do later on. It's trivial if it's just a row. It's a bit more difficult if it's a column. Okay, and of course this can also be done in parallel, because basically while I'm exchanging information, of course I can do that. Okay. So basically the communication here is to send data into Halo storage. So essentially what you will say is, okay, I'm going to create a boundary somewhere, an extra array, and that contains the Halo information. So essentially that contains information which will be passed into via a message. That's essentially the idea. Okay, so the serial code will be here. X new is just a function of X old. And then we just update the value of X old with X new. That's the serial code. It's very easy. If this gets parallel, of course, then things get a little more interesting, because now we have a lot of these guys. And of course, what we can do is X old. Okay, boundary conditions, we have to distribute them. Okay, let's forget about boundary conditions. That's not particularly interesting. But basically, X new needs to be updated everywhere. So essentially, what you would get is first you update the Halo. So essentially, you exchange all this information. And of course, if you have a 2D grid, it means that you need to send, in general, 4 messages. One up, one down, one left, one right. That's essentially the idea. And you also need to receive 4 messages. If you do that in 3 dimensions, of course, it goes up to 6. To 6. So basically, that's the number of messages you need to send. You don't have much choice there. Okay, so then we have, again, we can compute X new. It will be based on X old, and also, of course, on the Halo information, which we exchanged in the previous step in this procedure. And then, again, we just update X old with the values of X new. So what gets inserted here is the update, so essentially the Halo exchange. That's the new guy here. Apart from that, it's the same code, you could say. Okay. So that's essentially the idea. So if we put that into code, again, it's in C. So we have the global lower bound and the the global lower bound and global upper bound. Okay. So basically, then we have, so that gives us our dimensions. And then, we have the time loop. Okay, so we've got a numerical function that computes X new based on X old, and of course on these begin and end indices, which are global. So essentially, that is 0 and -1. We're talking C, so basically arrays in C are the first index is 0, the last index is the length of the array -1. So Note that actually translated our two-dimensional example, which is a bit more visual, into a one-dimensional example here. Okay, never mind, same thing, just a bit less complicated. And then we swap values of x new and x old. Okay, so nothing special here. The semicolon for the Fortran people just separates several statements. That's the idea. Okay, so now we need to add some stuff, and the stuff we need is the Halo communication. So as usual, we have an MPI init and somewhere an MPI finalize, which is missing, but okay. So basically we do the MPI comp size thing, the comp rank thing. This is something you always do because you almost always need that information anyway. So that's usually what you start with after the MPI init. Okay, so then, of course, now we're in a distributed memory setting. So essentially, while we had one very large array to start with say n elements, now, of course, each process has less elements to process. So each process can now communicate its own lower bound and upper bound. So this IB local and IE local. Okay, so basically that's done based on the rank. So this is essentially the size, so this is just n essentially. We divide that by the number of processes, and to make sure we get no problems here with the index, so that's why the +1 is there. And then we have the local end index, which you have to be a bit careful with. The minimum operation is here in order to make sure that if size doesn't divide n, you have to make sure that you don't get an array boundary which is, or an index which exceeds the array boundary. So basically, okay. Then we compute the left and the right neighbor, and we can of course do that based on rank, because essentially if I'm rank 5, my left hand neighbor is going to have rank 4, my right hand neighbor is going to have rank 6. So the only thing I need to do is to add 1 for the to get the index of the, to get the rank, I should say, of my right neighbor. I should subtract 1 of my own rank to get the left neighbor. Okay, all that works, except of course for rank 0, because then we would get rank -1. No, I don't think so. And of course for rank the number of processes -1, that's also not going to work. That's why the trick is here with the modulo. So basically this ensures that you will actually have the right index. Okay, left and right. Okay, so these are my neighbors. And then we have, in fact, a combined send-receive operation. We'll go into the details later. But given that left has to receive something, but left also has to send something, you can combine the two. And that's what's happening here in the send-receive. So send buffer stands for the let's x old, okay, and we're going to this is a certain thing here, so basically this guy, okay, and it's going to send it right. This 111 we'll discuss later, and that's going to be sent left. And the same is going to happen for the other part. So basically, for this guy here, where is it? For this guy, in this case, okay. So basically, we are doing two operations in one here. We'll go into the details later, but that's essentially the Halo operation, and that's something that is very common. So that's a bit of a running example here. We send stuff left, we receive from left. We send stuff right, we receive from right. That's basically what happens here. Okay, so as you see, we need quite a bit of stuff here. So of course we're not going into the details. Okay, I think I'm going to skip this here. Okay, maybe something to draw your attention to. Of course, there are a number of ways in order to deal with the fact if your domain doesn't is not really divisible by the size. Then you can do several things. So basically, what you saw in the example code was that the last process would potentially have less data than all the other processes. So, for instance, if I have 17 and I have to divide that 17 array elements, have to divide them over 4 processes, I can do that in many ways. 2 ways make sense. I can either say, okay, I'm going to assign the maximum each time to a process, and then the leftover. So basically, in this case, I would get 5, 5, and 2. The sum is 17. Or I can do that slightly different. I can say, okay, I'm going to assign round robin. So 1, 2, 1, 1, 1, 1, 2, 2, 2, 2, until the thing is filled. And then I get 5, 4, 4, 4. Okay? Sum is again 17. No difference. The only thing, of course, is that in the first case, I would have one process that needs to do 2 things, and all the other processes need to do 5 things. So that last process is always going to wait. And it's going to wait for quite a while. Okay? So the second distribution, now everyone has to do 4 processes except for 5 for the first one. First one has to do 5. So that means 3 processes are going to wait, but they're only going to wait for 1 unit. While here, this process is going to wait for 3 units. So depending on what you need, what you want, this might be the better option. Okay. Let's not go there. That's just a little bit of arithmetic, so let's not do that. Okay. So you asked about broadcast. So let's go into that example. So broadcast is a collective operation. So it's one of a class of communication operations. So collective communications are higher level. Why? Well, essentially, you could ask, okay, why do I need broadcast? It's not required. Because what I can do is just say, well, fine. If process 0 wants to communicate a value to all other processes, that's quite simple. The only thing it needs to do, it needs to send a message to each other process. Each other process just does a receive for a message that comes from process 0, and you're done. Why do we need this broadcast? Okay. Trivial reason, it's something that happens a lot. So basically, if you were forced to implement a broadcast over and over again because you need it several times, that would be a little bit annoying. It would also be quite error prone. So those are trivial reasons to define a function, a procedure to do exactly that, a broadcast. Okay. But there is another reason as well. Basically, it offers opportunities for the writers of the library to actually do some optimization. You might ask, okay, how on earth can I do optimization here? Because I need to send n-1 messages. How am I going to optimize that? Can't do that. Well, actually, yes, you can. Because what you could do is say, well, okay, process 0 is not going to send messages to all processes. Let's take as an example that we have 8 processes. So if process 1 would send a message to each process, that would take 7 units of time. It needs to send 7 messages, so it would take 7 units of time. All right, let's see whether we can do better. Suppose that process 0 sends to process 3, process it's easier if I draw it. I'll do the numbers for the people online, but it's easier for me to visualize when I draw that on Blackboard. Otherwise, I have to do that in my head, and that's also easy. So I've got process 0, 1, 2, 3, 4, 5, 6. That was so good. Okay, I can do it with 6 as well. I don't care. So basically, what I can do is send a message from process 0. I can send a message to, for instance, process 4. Okay. And then it's process 4's task to send messages to these guys here. Okay. I can also send a message to 2 from 0. And then it's 2's task to send a message to 3. And finally, 1 also sends a message to 1. So how much communication do we have? Process 0 has only sent 2 messages. Okay. Process 1 didn't have to do anything. Process 2 has sent a single message. Process 4 has sent 2 messages. Okay. But process 0 sending messages, process 4 sending messages, process, what was the other sender? 2 sending messages, that can all happen simultaneously. Those are just messages on my communication network, so that happens simultaneously. So, of all the processes, the maximum number of sends in this particular case was 3. So basically, process 0 spends only 3 time steps, 3 units of time in sending. All the rest spends less. So we go from 7 units of time to only 3 units of time. Okay, what's the more general pattern? And the reason why I actually wanted 8 rather than 6 is okay. If you start drawing things badly, then you run into your own stupidity. So basically, the idea is that you send communications essentially along a binary tree. And of course, you know that the depth of a binary tree with n leaves is in fact logarithmic base 2 of n. So essentially, if I have 8 nodes, if I have 8 processes, I should say, the logarithm base 2 is 3. And indeed, with 3 messages, I can actually, for one process, I can actually reach out to all these 8 using other processes in order to forward the message, if you want. So that's essentially the idea here. So I go from ON, number of processes, to O log n, which is of course much better. For 8 processes, we don't care. But if we have 1024 processes, then it gets interesting. If I wouldn't do this optimization trick, it would take 1023 units of time. I would have to send process 0 would have to send 1023 messages. Okay, but using this division of work trick, using a binary tree, I get away with the logarithm of 2 of 1024, and that's 10. So there is no process that sends more than 10 messages. So the total duration is 10 units of time rather than 1023 units of time. Okay, that's a factor 100. Now we're talking, now it gets interesting. So that's also why these collective operations are a very good idea to use them if you can, because MPI library implementers have done quite some thinking about how to optimize them. And of course, you could do the same with your MPI send receive. But first, it would require a lot of thinking. And second, it's easy to get wrong. And third, why would you if it already exists? Okay. So that's why collective operations are in fact very useful, and why most of your communication is in fact done using collective operations. Even for this Halo exchange, we'll see that there is a sort of collective operation. Okay, so that's quite a lot of explanation about this third sentence here. And well, basically, I also meanwhile showed you how this can be done with point-to-point communication, if you want to, or in an MPI library, more low-level primitives might be used as well. Okay, so conceptually, broadcast is just taking a horn and shouting. That's the idea. One guy shouts, the rest hears that. But there are other collective operations as well. So broadcast is in a way the simplest one, if you want. So another one which is quite useful is a reduction. So everyone's got a value, and you want the sum of those values. Okay, that's a reduction operation. And for that we have MPI reduce. So that is another one. There are also barriers. So you will remember that in OpenMP we have been talking extensively about implicit, explicit barriers. So you also have an explicit barrier in MPI. It's just MPI barrier. Semantics is quite simple. So everyone starts running and waits until everyone has arrived at the barrier. Then the barrier opens and they can continue. Okay. Wolf did have too much time when he made that slide. Anyway, so yes, barriers exist. Should you use them? Be careful, because they cause synchronization. Synchronization is costly, and you might create a load imbalance here. So in MPI, typically, you don't use barriers because you don't need them typically for communication, as you would need them in OpenMP. But they can be useful, for instance, for debugging. They can be useful for timing. So those are two very valid use cases for MPI barrier. But in production code, typically, you don't need a raw barrier. We'll see an example with a non-blocking barrier, but okay, that's a different story later on. Okay. Then another very important aspect of MPI is MPI I/O, so I/O in parallel. And this is a motivating slide for that. So basically, unfortunately, I/O is increasingly getting more important in the context of HPC. That is unfortunate because it's something we don't want to think about. It should be simple, and it's not. But let's motivate why it's actually important. So we do a computation on one core, so that's essentially sequential, or we do it with 64 processes on 64 cores. And we do that computation in parallel. Okay. So suppose that the computation part, and that's the second column, that the time for one core is 64 minutes. Okay. So if we're lucky, we hope And of course, the same computation using 64 cores takes only 1 minute. Okay, ideal case, blah, blah, blah. But let's assume that, no problem. Now, of course, there's also some time to do I/O. And in both cases, so both for the sequential as for the parallel implementation, the I/O is sequential. That's the assumption here. And it takes just a minute in order to write the results to a file. Okay. And that, of course, doesn't change from sequential to parallel because we do our I/O sequentially. So that 1 minute remains 1 minute, whatever we do in parallel. Okay, but now look at the numbers. So basically, if we have a sequential application, more than 98% of the time is spent on computing, and only 1.5% of the time is spent on I/O. Okay, that's fine, I don't mind. But now, of course, if we run that in parallel, things get different. Because now we spend half the time computing and half the time on I/O. That's not so acceptable. So that's why actually I/O gets important, especially if you have many processes, because if your I/O is sequential, that most likely means that all the processes are waiting until one process finally finished writing that file. So basically that means that quite a lot of very expensive hardware is just sitting there twiddling its thumbs and waiting for some stupid file to be written. So that is essentially the problem here. And that's why where MPI I/O comes in, because basically that is where you want some gains, where you want to do things more efficiently. Okay. So that is something that we will also discuss. Okay, so this slide, these slides, rather cool, were also in the presentation on OpenMP, so sorry about that, but I will repeat them nevertheless, because it's important anyway, and not everyone has attended the OpenMP training. So one of the things that you want to know when you are parallelizing an application is how successful are you? What are your gains? And there are several measures in order to quantify them. And the very simplest measure is essentially the speed up, the parallel speed up. So what do we have? We have TPN, and that's basically the time it takes to solve a problem of a size n with p processors. That's just the definition. Okay, what's that size? Let me make that concrete for a number of examples. So for instance, if you're in molecular dynamics, then this problem size might be the number of particles you consider, for instance. If you have some CFD computation, the n might represent the size of your grid. So basically n defines the problem size. Okay, and p is the number of processors, for instance, MPI processes or threads in, or both, depending on what you're doing. Okay, so we can define the parallel speedup for when I use p processes on a problem of size n, then that's actually just the fraction of solving the problem with one processor and solving the problem with p processes. So we just compute the fraction of the time that takes. Okay. So that means ideally, if I have a problem of size n and I have p processes, that ideally my speed up will be equal to p. That would be the ideal case. Okay. So yes, that's a measure for measuring how well you do. And then a very related quantity is the parallel efficiency, and that's just your speed up divided by the number of processes. Okay. Easy. Given that the speed up at best is p, that means that the efficiency at best is 1. So the efficiency is something between 0 and 1, or 0 and 100%, depending on how you want to look at it, but that's essentially the idea. Okay, so we are computing here the same problem, same size, same problem, but with more resources. So that's what both speed up and parallel efficiency measure. If you report something, if you're asked how does my code scale, please give parallel efficiency, don't give speed up, pretty please. Why? Because from the efficiency, you immediately see how efficient things are. From the speed up, you have to still calculate it, and there is some thinking in between, so it's a little bit less obvious what's going on. The speed up might be quite impressive. If I just tell you, okay, my application runs 100 times faster when it's parallel, yeah, that's great. And now please give me the efficiency. So if I need 1,000 processes to get this 100-fold speed up, that's nice, but then I have an efficiency of 10%. And that's not really very impressive, is it? So that's why personally, and most people in the business, let's say, prefer parallel efficiency to speed up, because you immediately see how efficient things actually are, how effectively you're using these parallel resources. Because essentially it means if you have 0.1 efficiency, that means that 90% of the time nothing is happening. That's cool, but cool in the sense that, okay, that saves on energy, and hence, yes, it's cool because your processes get less hot, but yeah, that's not what your taxpayer is giving you all that money for. So basically, that is not a good idea. Okay. Now that's one measure, and we will see why actually why there is a problem with that, which we circumvent by doing things differently. Because, of course, it's one thing to try to solve the same problem faster, but we can also do something else. We can increase the problem size and also use more resources to solve that problem. So we just solve a problem, a larger problem with more processors. That's another way of scaling up. And that's why this is called scale up. And now, essentially, what we're going to do is we define the because lowercase n is not defined, so n is a small problem size and n is a large problem size. So basically, yeah. So basically, what we want to do is we want to, if you can compute a problem of size lowercase n, so that's a small problem, with one processor, then we want to see whether we can compute a large problem, uppercase n, with p processors. If this time is the same, then we get the scale up. So in other words, if I can solve a problem of size 1000 with one processor, in the same time as I can solve a problem of size 2000 with two processors, then of course my scale up would be 2. 2000 divided by 1000, provided the time is the same. So that's essentially the scale up, and that's computing a larger a larger problem with more resources in the same time. So that's your scale up. Okay, and then you can also report something else, which is weak scaling, and essentially this is the time it takes to solve a small problem with one processor, that's in the denominator, And in the numerator, you've got P processes, and you compute a problem that's P times as large. Okay, so basically we scale the problem and the resources simultaneously. In other words, suppose that I've got the time it takes to compute with a single processor a problem of size 1000. Okay, again, suppose that I use 2 processors, then I measure the time it takes to compute a problem of size 2000. And then if I got weak scaling, then this is going to be close to 1. Okay, that remains constant. If this drops, then of course I have bad weak scaling and I have an issue. Okay, so there are a few things. So essentially, how does this relate to the clock frequency of your machine? It's not always clear because a number of problems have to do with the memory. And that is illustrated because in some circumstances you get actually superscalar scale-up or superscalar speed-up. So that means your speed-up actually is larger than your number of processes. Okay, so that may happen due to memory usage. You have a whole cache hierarchy, and depending on how that data gets used by your program, these caches can actually help you. And due to the fact that the problem size gets a bit smaller if you spread it around, it means that more of it can fit in cache, and that actually you would see a speed up which is a bit larger than P, or an efficiency which is larger than 1. So you may see that. It's not exceptional. It's also not commonplace. So basically it happens, but it's not as if it's true for each problem. It depends on what you're trying to do. But that's something that you have to realize essentially. Okay, so basically the question is, how well can we do our speed up? How much speed up can we actually expect? Or which efficiency can we expect? So we can expect at most the speed up of P, this we know. But does this scale? I mean, if I keep on increasing P, will the speed up also still increase? The answer to that is unfortunately no, and that's just a bit of mathematics to prove. So, what do we have? We know that TPN, so basically the time to solve a problem of size n with P processes, consists of 2 parts, always. That is the time that is actually doing things in parallel. And then, of course, if we do things in parallel and we assume that this parallelization is perfect, so we don't have any overhead, then the time we spend doing parallel stuff, or stuff that can be parallelized, we can divide that by number of processes P. But there will always be a fraction of our code that we cannot parallelize. So the fraction of that runtime is in fact lowercase f here. Okay, so we can decompose the total time with P processes into the fraction of the execution time that is always done sequentially, because we can't parallelize it, and the fraction which we can parallelize. And of course, that should be 1 minus f times the time that takes, which is t1 n divided by p. Okay, so this is what we have. But then, of course, we can compute the speed up, and you see what's happening. If we do the math here, then we get, for the speed up, 1 divided by f plus 1 minus f divided by p. And you see where that's going mathematically. If I let p go to infinity, then, of course, the problem is that this term here vanishes, but we will still have 1 over f. So the speed up is in fact limited to 1 over f. So basically, I can keep on adding processors, I can try to run it on more and more hardware, but my speedup is never going to be more than 1 over f being the fraction of sequential compute time. Okay, that's nice. No, it isn't, but how alarming is this? Well, let's compute the speedup in various cases. So in the ideal case, as I already mentioned, the speedup is just p. Okay, that's the diagonal line here. I think it's green. So that diagonal line here. So now let's consider fractions of our code that are in fact serial. So in the first case, f is equal to 0.1%. So a very small fraction of our code cannot be parallelized. And that's the curve just below here, so this guy here. And as you can see, even for just 100 processors, we have a speedup of only 90 rather than 100. So it drops pretty fast. If we have a 1% fraction of serial code, then you see that we end up here at a speedup of 50. So an efficiency of 0.5. And of course, if you get to 5% or 10%, the situation is really, really bad. For instance, for 10%, yeah, you end up with a speedup of 10. Basically, that is not particularly good because that's an efficiency of 10%. Okay, and this is pure mathematics. There's nothing you can do about that. So this is the problem with strong scaling, and that is called Amdahl's law, which is a little bit depressing. Okay, fortunately, that's usually not what interests us as scientists, because what we typically want to do is to solve larger problems, to get more details, to get more molecules, etc., etc. And then, of course, what interests us is not so much strong scaling, not how can I solve problems faster using more hardware, but how can I solve larger problems using more hardware? And that's where the scale up and the weak scaling comes in. So basically, that is the message here of this particular slide. Okay. All right. So that's a little bit what you have to keep in mind when thinking about efficiency and about parallelization. This lowercase f is an important thing. You have to get that as small as possible. And one of the ways to do that is to make sure that I/O is a parallel rather than sequential. Okay, so who owns MPI? Well, there's an MPI forum, and that's a body that defines the MPI specification. Basically, there was an MPI1 forum, and as you can see, the first specification was published in 1994. So MPI is pretty old. It predates OpenMP by, I think, 4 years. There were other similar things before, but they died, so basically. Then we got to MPI2. So basically you can see the dates here, I hope. No, there are dates, but not for MPI2 apparently. So things evolve. 2008 we got MPI 2.1. 2012 we got MPI 3. And yeah, that was the train-the-trainer thing at the time, because MPI 3 was just published, as I recall. So that must have been October 2012 when I followed that training. And then you see the standard further evolves. MPI 4 was published in 2021, and let's say some minor details were changed in MPI 4.1 in 2023. And of course, it's an evolving standard, just like OpenMP, so things get added, but things get also removed. Things that turn out to be a bad idea get deprecated, and after a while, they get removed. Okay, so basically, what's the idea? well, you want to provide a message passing interface. That's what MPI wants to do. It wants to define that, to specify that. Okay. What it also wants to ensure is that if you write an MPI application, that it will work with any MPI implementation. So that's what's meant with source code portability. Okay, and of course, the specification should also be written in such a way that it's at least possible for developers of MPI libraries to provide efficient implementations. That's the idea. There is really a lot of functionality. And what it also does is supporting heterogeneous parallel architectures. So basically, you can even run processes on different types of hardware in the same application. That is an option. Whether you should do that is a different matter, but okay. All right, so basically MPI 2 offered quite a lot of important functionality, same in 3, etc., etc. But you see that from 3 onward, things were actually getting deprecated as well. So design choices which were made in the early days turned out to be suboptimal. For instance, because efficient implementations were hard or impossible, and they got deprecated and will be removed from the future versions, essentially. Okay, all right. Basically, this is not a very interesting slide. We are not going to do a quiz. Homework. Okay. Right. So we have already seen an example for, or several examples for C and one for Fortran. So one of the things which is important is how do you use, from your favorite programming languages, how do you use MPI? And of course, language bindings, that means there are functions, there is an API defined for C, there is an API defined for Fortran. That's all in the MPI specification. And there are also bindings for Python. Okay, so header file, or where do I get my declarations from? For C and C++, that's quite easy. Include mpi.h. Okay. For Fortran, use MPI F08, preferably, or use MPI. I would suggest, if you can, but we will come back to that in detail, to always use MPI F08, because it guards you against quite a number of very annoying mistakes you can make, and very bad mistakes you can make. In Python, you just do from MPI for Py, import MPI. Okay, so that's easy. All right, then the MPI function format is very uniform. So most MPI functions follow the same pattern. With respect to naming, they always start in C and C++ with MPI underscore, and then a capital letter followed by all lowercase. That's for the naming. There are also some, well, okay, you can, of course, ignore that return value as usual, and then it has a number of parameters. So that's always the case in C and C++. One of the things that you never ever should do is have functions of your own that start with MPI underscore, etc. Don't do that. It's a very bad idea. Why? Because there are 5 million MPI functions, and the probability that you name your function similar to one of those may exist. If you do that, you're going to be in very deep trouble. So the MPI specification says you can pick any function name you like for your own functions, as long as it doesn't start with MPI underscore capital something. So don't do that, it's a bad idea. Okay, so for Fortran, it's mostly subroutines. So we have call MPI, etc. MPI underscore something something. As you know, Fortran is not case sensitive. So what I typically do, because I regularly switch languages, I will use the same capitalization convention as for C. It doesn't mean anything in Fortran, but I do it nevertheless because then I need to remember only one thing rather than two. But you do whatever you like in Fortran, of course. And then in Python, in fact, you have method calls on your communicators. So basically, you work directly on your communicator. So basically, you have a send method on your communicator, you have a receive method on your communicator. So things work a little bit differently. And that's similar to the old, but deprecated C++ bindings at the time. Okay, so MPI functions return an error in C and C++, an error value. So that's just a number, it's an integer. And all the Fortran subroutines taken as a last parameter, they also take an error. And that's of course call by reference. So basically that will be updated by the call. Okay. Now, if you do use MPI, always remember to add that argument, that parameter. Because if you omit it, your Fortran compiler is not going to complain, but you may get a seg fault down the line. So in Fortran, that's a very bad mistake. Don't ever forget it, unless you use MPI F08. So if you use that one, then you don't have to do this anymore. We'll talk in more detail about that later. Okay. So basically, this is more formally what it is. So constants typically are in all uppercase. So for instance, the constant MPI conworld is written all uppercase. Functions are typically MPI capital, underscore X lowercase, and perhaps more underscores. The same for types. So functions types are the same, and so MPI constants and so on, language independent things and so on, they are all uppercase. So that's basically the idea. Okay. So this is again the error thing. So if you use MPI or you include MPI f.h, don't do that, but okay. Then you have to remember to get the error here. If you don't have the error, you have a rather awful problem. You don't have to do that anymore if you use the new module, the new Fortran module, so the MPI underscore F08. So for new development, if you start writing a new MPI application, just start with this use. Very simple. If you have a legacy application, which for some reason uses MPI, then don't forget this error, because if you forget it, you're in deep trouble. Okay, so a bit more details. So this is for C and C++. Essentially, of course, you know that in C and C++, everything's called by value. So if you want the semantics of call by reference, what you do is you pass in the address of the variable. So basically, you pass in a pointer. And that's exactly what happens here in this MPI com rank. You pass in the address of an integer where you want to store the rank. Similar for other things that you want as output arguments. Okay, So here's an example. I've got my rank. If I do MPI.com rank, I have to pass in the address of my rank, which basically means I use the address of operator, which is the ampersand. Okay. So that's a bit more annoying if you are into, if you're using C or C++, you have to be familiar with pointers. If you're not, you'd better read up on that, or things will be a little mystified and mystifying. Okay, let's not go there. So this is what I meant. So this MPI underscore namespace, that's reserved for MPI. Specification says don't do that. You might confuse things, and that is important. Okay, so about MPI for Pi, we can be very brief. It's not part of the specification. What is actually happening is that the MPI for Pi developers write wrappers around an MPI implementation. They do that using Cython, and they really take care to minimize overhead in these bindings and so on. It's a really interesting software engineering project, but basically you don't have that kind of issues there. Or you have different issues, let's put it that way. Okay. This is actually a screenshot, let's say, of the MPI specification. And this is the pattern which is always followed when you look up a function in the specification. So the first thing you have is a language independent format. And as you can see, you have in and out here. So these are the things that the out are the values you want to get. The in is the parameters you provide. So they're read only. So in is just reading, out is writing a parameter in a function call. So basically, let's see whether that makes sense. We have MPI receive, okay. The buffer is out. Yeah, indeed, because that's where I expect the value which has been sent to me, which I'm receiving, to be. So that must be an out parameter, okay. Then the count, yeah, I expect a certain number of values, so that's something I specify, it's in. Same for the data type, same for the source, same for the tag, same for the communicator. And finally, the status is also something that's an out parameter. Okay, so that is the general documentation, so the language agnostic specification, if you want. So how does that translate? For instance, into Fortran, well, basically, into C first. Here we have the C interface. And essentially, everywhere where there was an out parameter, you will see that an address is expected. So that's each time a pointer. So that's easy to translate. And then for the Fortran 2008 interface, what you will get is the intent. So essentially, everywhere where there's an in parameter, there is going to be an intent in. You see, and then for the other parameters, the intent is in fact out or in out. Okay. What you also see is that the error for that interface is optional, and it also has intent out. So basically, thanks to the optional, you don't have to specify it. If you don't, it's not a problem. In the old Fortran interface, you see a few differences. You see that there is very little type information. Nearly everything is in fact just an integer. Okay. While here we have a distinction between, for instance, the communicator in fact has its own type. It's type MPI.com. So that also helps the compiler to track down errors. Because you can imagine if everything is an integer, like it is in the old style Fortran interface, then if I swap around the data type and the count, compiler is not going to help you. both are integers, so it doesn't care. But if they're different types, while here, for instance, the count is an integer, while the the data type is an MPI data type, if I now switch them around, the compiler is going to say, oh, counts don't match, and to catch mistakes. So that's another advantage of the new MPI interface, so the MPI F08. So definitely use it if you can, for these two reasons. The horrible stuff you get when you forget the error, and also your compiler gets more information, so it can help you detect things that you are not doing correctly. Okay. So basically, let's not go into the details now. That comes back later. But this is what you will always see in this MPI specification. It's always the same format. Okay. So initialization of MPI, we've already mentioned that. You just call MPI init. And in C, C++, you can pass in the address of argc and the address of argv. So basically like this. This is your MPI init call. Okay, so in Fortran, that's easy. You just do MPI call MPI init, potentially with an error, or not if you use MPI F08. Then you can just do MPI init without arguments, call MPI init without arguments. Okay, so how do you do it in Python? You don't. In Python, you don't have to do MPI init. Why? It's simply done automatically for you on first import. So the first time we're going to import, it's going to do a call somewhere to MPI init. So you don't have to worry about it. So that is quite convenient. And that also means that unless you do weird things, you're sure that MPI init is going to be called before you actually do anything that makes sense. All right. Then I already mentioned that stuff does get deprecated, so that's something to keep an eye on. So as you can see, MPI F08 is there to stay, but use MPI is at the moment already strongly discouraged. And it's in fact deprecated in MPI next. So it will be officially marked as going away in whatever is following MPI 4, so probably MPI 5. Okay, the include MPI f.h is actually also very strongly, well, it's deprecated today, and it will vanish most likely in the future. So that is something to keep in mind, and that's also something to keep in mind for other things that are deprecated. Okay, just to point that out. All right, then to finalize the whole MPI thing, so that's the last thing you do in your MPI application, you just call MPI finalize. And remember, everyone has to call MPI init, everyone has to call MPI finalize. All the processes have to do that. Okay, again, the usual mantra. The error is optional, so I can just do call MPI finalize in Fortran, no problem. Okay. So of course, after MPI finalize, don't do any MPI calls. You can do that. Compiler is not going to complain, the linker is not going to complain, only it's not going to work. So don't do that. And especially don't try to do another MPI init. So what you can do is MPI init, MPI finalize, and then another MPI init and MPI finalize. That's absolutely no-no. Okay. So basically, there are some alternatives in MPI 4, but yeah, that's something that we will discuss tomorrow, most likely. All right. So essentially, what MPI init is doing is, how you start your MPI process is implementation dependent. So that is the MPI run, MPI exec. There are a couple of possibilities there, but what you can be sure of is that if that thing runs, then everything is ready. Your process can communicate. Your process has been started, and everything is ready to start communicating. That's the idea. So after, of course, MPI init. Okay, so that's essentially the idea. And as you can see, we can do MPI run with -np or MPI exec with -n, depending on whatever your MPI implementation offers. Okay. Time for another exercise, but let me have a look at the time now. Okay, yeah, that's not bad timing. So let's perhaps do an exercise, and let's do an hello world. So essentially, this is sort of a easier case of the previous exercise, which we already did. So in this case, I'll do it in C, but feel free to do that in Fortran. So I include mpi.h. I've got my main. I want my rank, and I want number of processes. And that's, in this case, actually enough. I don't need more. And then, of course, I need my MPI init and the corresponding MPI finalize. All right. This is what I usually do when I start writing an MPI application. I always do it in pairs. So the MPI init, and I immediately write the MPI finalize. Because, of course, if you don't do that, the probability that you will forget it when you've finished your main is non-negligible. So I prefer to do it immediately in pairs. Okay, then what we typically always need is to get our rank and our size. Okay. So note for the C people, I'm passing in the address of my rank variable and of the number of processes variable. So that's what the ampersand is for. It's the address of operator. Okay. And then if my rank is equal to 0, I'm going to write the number of processes. And in any case, each process is going to print this message. All right, so that was easy. My compiler is not happy. Well, I get a syntax error here because it says, okay, I can't find mpi.h, but that's simply because the compiler which is being used under the hood is simply a C compiler, and it doesn't know where to find the mpi.h. So that's why I get the syntax error, but actually there's nothing wrong with it, unless I mistype something that I don't see now, but normally that should be okay. All right, so essentially that would be it. So let's compile that, MPI CC in this case, and hello world or hello.c. Okay, it compiles. MPI run -np4 a.out. Okay, so as you can see, this is more interesting output than before. I do get 4 times hello from, and indeed I get it from process 0, process 1, process 2, and process 3. So that's good. The 4 processes in total, that's correct. And also process 0 has written that there are 4 processes. Okay. So if I run that again, you see that I get something similar, but not quite. So in this case, first process 0 has written, and then they all write in order in this particular case, but that is coincidence, because if I run that yet another time, I will get again different output most likely. Yeah, as you can see now, first processes 2 and 3 have written, then process 0 has written, and then process 1 has written. So the output is non-deterministic, and I'm guessing that you're not surprised that that's the case, because basically, depending on how these processes start, where they run, etc., one is a bit faster than the other. At some point it will be process 0, which is the fastest. At another point it will be process 3, and so on. And of course, with the more processes I run this, the more prominent that's going to be. So if I run it with 8 processes, you see that I get something which is a little bit weird. First 2, then 4, then 5. So as you can see, the order is pretty much random. Okay, so I guess that doesn't come as very surprising. Is this working out for the Fortran people? Or should I also do the code? Let's maybe quickly do the code. Okay, so program hello, and program hello, use MPI F08. In this case, I'm not going to do anything with typing, so I'm not going to include the ISO Fortran env thing. Okay, I need only 2 variables, which is my rank and number of processes. Okay, so that's my setup. Then of course I have to call MPI init, and I'm using the MPI F08, so I don't need to provide the error parameter. Don't have to do that. Okay, similar as before. I immediately do the finalize, just not to forget it. And then I need the value of the rank, the value of the number of processes. Okay, so if my rank is equal to 0, and then hello from number processes, okay, and if, and otherwise hello from process, okay, and to make it similar to the other example of number of procs. Okay, so same, but different. This should do the same thing. Okay, let's see. MPI F90 and hello.f90. Okay, MPI run dash np4 a out. Okay, so indeed we get 4 times the value printed of the process. 0, 1, 2, 3. That's good. We have 4 processes in total, so all looks good, except for horrible output formatting. It's just a default, so yeah, you know the drill to get that nicer. I'm not going there, but basically you see it's the exact same thing. So MPI init, MPI finalize, get the rank, get the number of processes, and get going. That's easy. Okay. I could try to do the Python thing, but I have to be a little bit careful. And I'll tell you why in a minute. The problem is if I will have to activate some Conda environment in order to get MPI for Pi. I don't have that, obviously, just brute force installed on my machine. That would be very bad practice. So basically, I need to load an environment, but that environment is likely to contain quite a lot of stuff I don't want, like other versions of compilers and so on. So that would be a rather big problem. So let's activate an environment. Activate, let's try to do that right. Python for HPC. Okay, so this certainly contains MPI for Pi. Let me go to the same directory as I was in, just to keep things contained. Hello.py. Okay, so let's make this executable. The usual user bin env Python. Yeah, I don't need the 3. There is nothing. There is no 2 anymore. So, okay. Then from MPI for Pi, import MPI. Okay, that already takes care of my MPI init, and by the way, also of MPI finalize. Okay, because this is running in a context, and basically that is okay. So I can define a main function if I want. Actually, I don't really want to go there. I actually just want a communicator. MPI com_world. Okay, then I want my rank. And I want number of processes. Okay. And I want to do the same thing. If my rank is equal to 0, then print hello from number processes. And any case I want to print hello from process of processes. Okay. All right. So that would be it in Python. At least I hope so. If I didn't make stupid mistakes. Let's see. MPI run dash np4. Oops. No, it's a single one. 4 and then my script. No. Let's make that. Well, it doesn't really matter, but I'll make it executable just to make life a little easier. Okay, and then I can do MPI run dash np4 hello.py. Okay. Okay. So that looks good as well. It's the same output as before. And as you see, again, it's non-deterministic what you get. If I increase the number of processes to 8, you see that also works. Okay, so that was very easy. So I would say, in general, MPI is reasonably easy to use. You need to know a lot about the API. Of course, you need to know quite a bit about parallel programming, but it's fairly straightforward to use. And in Python, it's also quite easy. It's even easier in general, and it's also, in a way, a bit more elegant than you would do in Fortran and in C. And in that respect, it's actually unfortunate that the C++ interface was removed, because that was also a lot more elegant than the C interface. But okay, whatever. It's difficult enough to maintain things with 2 standards if you have to include a 3rd one, especially one as complicated as C++, then it's really, really complicating things. Okay, so I'm guessing that okay, sorry, I was a bit too fast. So basically, one of the things that we've been using, and we've been using that in C, Fortran, and MPI, was this MPI world thing. So the question is, what is this actually? Well, technically, it's a communicator. And the communicator is the infrastructure, you can say, which you're using in order to exchange messages. So all messages are exchanged using a communicator. And when you start an MPI application, there is always a communicator, and that one is MPI world. So that contains all the processes in your application. It's guaranteed to be there. It's always there. And that is the first communicator which you use. And later on, you can define your own communicators, subcommunicators, or communicators that give you a different view on your processes. But anyhow, however you communicate, you're always going to use a communicator. So you can view that basically as the communication infrastructure, if you want. And so basically, each process has a rank in a communicator. It ranks always start with 0, and the last rank, of course, is n-1, where n is the number of processes in your communicator. Okay. So you get handles to this kind of thing. So you can view MPI world as a handle into that communication infrastructure. So it's a data structure, essentially, which contains a lot of information that you don't have to worry about, but that is used by all the MPI functions in order to do their communication. So basically, that is essentially the idea here. Okay. So yeah, I've been saying this a couple of times, so let's not go there. So there are quite a number of handles. One example is indeed MPI world, but there are also a number of different ones. They're always available, they're defined in either the MPI object for Python or in the header files for C and a module for Fortran. Okay, so if you need to type it, in Fortran, a communicator type is a user-defined type MPI-com. Okay, for C, there is a type MPI-com as well. Okay, so that is quite convenient. Then, of course, in Python, you don't really care about the type of things. You can check it if you want, but it doesn't really matter. Essentially, in Python, it's an object, and you can call all kinds of methods on it, like getRank, getSize, and so on. But also other things like split as we'll see later. Okay, so basically, all these things contain data about the communicator. They are internal. You never manipulate that data directly. You always do that using calls. So to get the rank, we've seen it several times, MPI com rank with the communicator and an out parameter, which is the rank. Similar for Fortran. And for Python, you just use the getRank method on the communicator object. Okay, quite easy. Then the same for size. No surprises here. For Python, you get size. Okay. Yeah, we know. So just a reminder, in Fortran, everything is a subroutine. Well, almost everything is a subroutine. So don't forget call, MPI. It's always difficult for me when I switch programming languages. The first thing I forget is, of course, to put the call there, because in C, a subroutine is in fact just an ordinary function, so you don't have to do anything special about it. Okay, so we did actually this exercise already before, so we don't need to do that. Okay, let's go into a little more detail about point-to-point communication, because what we have done is just use MPI send, MPI receive, but there were, on the one hand, a lot of parameters which I just said, well, okay, we'll see that later. And on the other hand, we've already discussed that there are various types of point-to-point communication: synchronous versus buffered, blocking versus non-blocking. So, okay, let's try to flesh this out a little bit and get a little bit more details. So what you are sending around as messages are essentially data values. And what you always have to specify is the type of these messages. So basically, that's the data type which there are. Okay, so there are two data types, let's say, the basic data types and derived data types. Derived data types is for tomorrow, but basic data types you can already do quite a bit on, and basically that we'll see tomorrow how to do that. So the C types are different from the Fortran types. So, for instance, an integer in C is MPI int. An integer in Fortran is MPI integer. Makes sense because an int in C is C, an int in Fortran is integer. So it just follows the convention of the typing in the language in which you're using the type. So basically, you describe the types not by their native types, but rather by type handles, which are defined by MPI. So if you're sending an integer, the data type is MPI int or MPI integer. In Python, basically, you can send around anything you like, not quite true, anything that can be pickled, you can send around. So that gives you a lot of flexibility and a lot of ways to shoot yourself royal in the foot as well. But you can also get different methods. So, for instance, if you want to send around NumPy arrays, you can actually use send and receive uppercase. So those have a different interface. We'll see examples later. But that allows you to send around NumPy arrays. So essentially, multi-dimensional arrays. Okay, so the basic data types for C and C++. MPI character corresponds to a character, MPI short to a signed short int, MPI int to a signed int, etc. MPI float is single precision, MPI double is double precision. You'll also have MPI long double, etc. etc. So basically, this is just a translation from your native type, if you want, to MPI type handles. Okay. Similar for Fortran, only the list is a lot shorter. So real is single precision. It's supposed to be single precision here, and that's MPI real. So this is a single precision number. MPI double precision is a double precision number. Okay. There are a few extra ones. So you do have MPI real 8, and that is then 8 bytes, so that's double precision. So you can also specify that one. And you might have noticed that my generative AI thing was actually suggesting this one. Okay. Now what I don't like on this slide, to be honest, is MPI real 8 for real star 8, because yeah, I would really not recommend using things like real star 4, real star 8. That's 8 style Fortran. Please don't do this. Use ISO Fortran env and use real 32 and real 64, which are defined there. But okay, that's a different discussion. Then we have complex. That's interesting because in C we don't have that. Of course, complex is a native citizen in Fortran, so it makes a lot of sense to have that, especially in the context of scientific computing. There is also logical. There is character. There is byte, and there is pact. So there are many similarities, but also quite a number of differences. So basically, we can either send a single value, or we can send multiple values. Sending multiple values means setting the count to a non-zero, to a non-one number. And that means I can, in this way, send part of an array or a complete array in a single send operation. So remember the Halo exchange? Rather than sending element by element of that top row, I can just send an entire row to the neighbor. In C and C++, in Fortran, I can send an entire column to one of the neighbors. Okay, so basically, then I would have a receiving buffer with the count as well. Okay, so for kind parameterized Fortran types, what you can do is create, to use MPI type create, F90 integer, real and complex. And that allows you to specify a kind parameter, such as, for instance, real 32 or in 64. So basically anything that's defined in your ISO Fortran env module, which gives you guaranteed portable types. So this is essentially the way to do that properly, rather than just relying on double and so on. So basically, you can just create your own type. And it's always a better idea, of course. All right, so now we kind of know what messages are. They are either a single value or a sequence of values stored in an array. And they can have any type, which was listed there. Okay, so now point-to-point communication means we have a source and we have a destination. The sender sends something to the destination, the receiver receives something from the source. Point-to-point, that's the idea. And these two processes need to be on the same communicator. So given that we have a single one now, they're both part of MPI common world. And of course, it's the rank in the communicator they have that they're using as source and destination. Okay, so what does it look like in more detail? So let's start with C. We have MPI send. Okay. Then we have a buffer. So that is an address. And we have a count. And we have a data type handler. So that's the definition of my message. So if I want to send a double precision number, which is stored in variable x, and it's just a single number, I would say, okay, address of X, so ampersand X, count is 1, and MPI double. Okay, so that's my message. Then we have the destination. So that's the rank of the process the message is sent to. Then we have a tag. Okay, I'll talk about that in a minute. And we have a communicator. Okay, so very similar for Fortran. We have also a buffer. Okay, we have a count. We have a data type. Same. And we have the destination, the tag, and the communicator. Okay, so again, suppose I have a single value, also variable x, it is double precision, then I will do MPI send x, count is 1, and MPI double precision, or whatever I do in order to get a type for that particular type. Okay, and then of course, the destination is the same thing. In Python, it depends. If I'm sending an object, I use the lowercase s method. I just specify the object I want to send. I specify the destination, and I specify the tag. Notice that in Python, there are default values for tag. The default is 0. Okay, so that already tells you that this tag can be useful, but that it's often maybe not really interesting. But we'll come back to that later. Okay, if I want to send a NumPy array, then I use the uppercase send in Python. Okay, so what I can do if I want to, maybe it's what I want to, maybe not. What I can do is say, well, okay, I have an array of 100 elements, and I only send 10 of them. I can do that, and the count would just be 10. And 10 elements will be sent. So I can do that if I want to. Okay, now the tag, let's talk a little bit about that. The tag is essentially kind of a label which you put on your message. And that means that if I set a tag on a message, at the receiving end, I can check for a message with that tag. So that allows me to, for instance, create different classes of messages. So I could have a tag for data, a message that contains data, and I could have a different tag for messages that communicate state. That would be one application of having different tags. But as the Python interface kind of suggests, very often you don't really care about these tags. It's nice extra, but it's not always necessary to do that. Of course, in Fortran and in C, you always have to specify a tag. Often it's just a constant which you define up front and be done with it. Okay. Now, receiving a message, the function signature is pretty similar. So we have MPI receive. Again, we have a buffer. So that's an address where to store stuff. We have a count, we have a data type, we have a source, we have a tag, and we have a communicator. And we also have status. So basically status, we'll see how to use that later. This can sometimes be quite useful. Okay, in Fortran, same thing. Nothing special is happening here. And in Python, again, we have two versions. One to receive NumPy arrays. We just have to specify a source, which we don't even have to. And we don't even have to specify a tag unless we want to. Okay, so this is interesting because this already shows us that we have a kind of wildcard. And we also have those in C and C++, by the way. Okay, and similar if you want to create an object. Okay, and then we can simply say, okay, if we don't specify the buffer, then it's just returned, and otherwise it is debris. So basically, it's even deprecated. So you don't really specify this. You just specify source and you specify tag. Okay. So basically, again, the buffer, the count, and the data type are describing the message as before. And then, of course, the source is the rank from which we want to receive the message. Okay. So what is the status? You might think, okay, success, failure. No, it's a bit more than that. It contains information about the message. So basically, what it will contain is, for instance, the count. And that's interesting, because that means that I can potentially, but for this I need probe, potentially I can create a buffer which is large enough, but that's for later. But that's one of the applications. If you don't want status, you can just use the MPI status ignore argument as a value. And then that just means I don't care about the status, I don't need it, so I don't want to use value in order, a variable in order to store it. So you can do that, no problem. Okay, so the output arguments, as usual, are buffer and status. Okay. So there is a message matching rule. So a message can only be received if the communicator matches with the send, if the source matches with the send, and if the tag matches with the send. So all of these things must match. So note that the count and data type are not part of this matching rule. In general, the send and receive have the same count and the same data type. Otherwise, most likely things are not going to make sense. But in theory, they can be different. Okay. So if you use uppercase send to send a NumPy array, that must be received with an uppercase receive to get a NumPy array in Python. And similar if you send around objects. So you can't magically turn a NumPy array into an object or an object into a NumPy array. That, of course, doesn't work. Okay, a number of requirements. On the one hand, we have the matching rule, but there are a number of requirements here. So the sender must specify a valid destination rank. That's pretty clear. And the receiver must also verify a valid source rank. Of course, otherwise you have a problem. The communicators must be the same, also kind of obvious. And then also you need some type matching. So the send buffer must match with the send data type handle. So basically, if I have a buffer which is an array of integers, then of course I would have an MPI int data type handler as its type. Yeah, that's pretty clear. Okay, the send data type handler must match with the receive data type handler. So if I send an integer, I'm also going to receive an integer. If I send a float, I'm going to receive a float. Okay. And then the third rule, the receive data type handle must be, of course, also fit the receive buffer. So if I specify as a type handle MPI int, then I need an integer buffer, otherwise it doesn't make sense. Okay, that's with respect to type matching. So at the end of the day, it just means float must match with MPI float here. Float must match with MPI float there, and MPI float must match with MPI float. That's data type matching. Then you also need tag matching. So basically, if I have a tag which I use for the send, I also receive that one. So it's the same number which I want to receive as a tag. Okay, so that must match as well. Okay, and then the receive buffer must be large enough. So essentially that means that the count at the send buffer must never be larger than the count at the receive buffer. Otherwise, I get an overflow. You can guess that things are going to go very wrong if you try that. Then part of the message is not received, so basically you have an issue there. Okay, so you can do data conversion as well in heterogeneous clusters. Frankly, I don't think you're going to do that. So essentially, let's not go there. Just remember that actually this can be done. I really don't think you will be in a situation where you have a heterogeneous cluster in this sense. Even if you have somewhat different hardware like Intel versus AMD CPUs or whatever, still this is not heterogeneous. So you can do it, but yeah, typically you don't need to bother with that. Just remember it can be done. Okay. Again, time for an exercise. So one of the things which you can do in order to see, well, okay, what's the latency of my network, is do pings. And the ping is just sending a message from one process to another process. So in this case, we will just have two processes, process 0 and process 1. And a ping is sent by process 0 to process 1. So it's just an arbitrary message. It can just be an integer or something like that. Okay. And then what we can do is we can measure the time between, we can measure the time it takes to send the message and receive the message. But let's not do that now. Let's just do first the ping. Okay. So let's do that in Fortran again. Okay, so much for generative AI. Maybe I mistyped and that's why it's confused, but okay. Of course, as usual, I'll need my rank. And I'm going to ask for the number of processors anyway. All right, and then I need my buffer. And I'm just going to, no, let's split that up. Let me explicitly do a send buffer and a receive buffer. Just to make very clear what's what. Then I also need a tag, so integer parameter parameter. Let's try to do that correctly. Tag is whatever, I don't care. Usually I use 17 because it's a prime number, so let's stick to that. Okay, do I need anything else? Yes, I need destination and I need a source and a destination. So integer source and destination. Okay. All right, so as usual, call MPI init, call MPI finalize. Okay, call MPI rank, call MPI size. That's the usual stuff. It's typically what you do very often. Okay, so now one of the things that you typically want to do if you have an MPI application is to make sure that it will run with any number of processes that you specify. So essentially in this case, in fact, I should abort my application if I run it with a single process only, because then of course the ping thing doesn't make any sense. And of course, what I should also do in this particular case is if I run it with multiple processes, I should make sure that there only is a single receive, because process 0 is going to send something to process 1. If I would use an if-else, and I would run it with multiple processes, I have a problem. Let me just type the code, and then, because then you will better see what I mean, why that's not a good idea. Okay, so I could do what's suggested here, actually, and just check that it's with 2 messages, but maybe let me not do that now. So I'm just going to check this, but at least. So, okay. Notice that we have something new now, and that new thing is MPI abort. And of course you can guess what that does. It's just going to terminate our application if we call this. So basically the MPI abort takes 2 arguments, the communicator, which is likely going to be MPI conworld in most cases, unless you do something very smart, but usually it's MPI conworld because you want your entire application to go down. And the numerical argument 1, that is just the exit status. So very similar to std exit in C and C++, or the stop with a number in Fortran. It's the same thing. But this is going to bring down everything. Okay, so that's my check. So I have at least 2 processes. So now what I could do is, okay, if my rank is 0, sorry, then I'm going to do an MPI send, and I have to initialize my buffer. So let's say buffer, send buffer in this case. I distinguish between the 2. Send buffer is, I don't know, my rank. Yeah, I can live with that. So that would be 0, of course. Okay, then we have MPI, call MPI send. Okay, we have the send buffer, the count is 1, it's an integer, so that's fine. We want to send it to 1. Yeah, okay, but let me make that explicit. So that will be destination. And I set destination to 1. And just for the sake of the argument, I'm going to put the definition of the send buffer here. Okay, now I could do else, and then my source would be 0, and I would call the receive buffer. Okay, so basically I'm not going to do all this right now, and I'm going to wrap my code a little bit. Received value, okay, receive buffer, and this I'm going to omit, this I'm not going to do right now. Okay. All right, so essentially that would be it. So quite straightforward. I'll send the message from source to destination. Okay, what's the potential problem with this?
multiple processes, more than two,
Yeah.
it might be that one gets in a deadlock mode because it's waiting to receive something that is only very soon.
Exactly. So basically, a problem will arise if I run this MPI application with more than two processes, because then a number of processes, process 2, 3, 4, 5, etc., will be in a MPI receive, waiting for a message that's never going to arrive, because process 0 is sending a single message to process 1. Process 1 is going to receive that message. Process 0 and process 1 are done. And process 2, 3, 4, 5, etc., keep on waiting for a message that's never going to arrive. Okay, so basically 2, 3, 4, 5 are not going to call MPI finalize, and your application is stuck. It's in a deadlock, indeed. So this is bad code. I should replace this with else if my rank is 1. Okay. Let's try and compile. Single ping. And let's run it. Just for the fun of it, let's run it with one process. Okay, MPI abort. Okay, this program requires at least two processes. Fine. That's exactly what we expect. Okay, with two processes, okay, process 2 received value 0. Indeed, because what we sent around was the rank of process 0, which is 0. Okay, boring. Okay, so this works, great. And now let's try what happens if I use 4 processes. As you can see, it happily works. There are 4 processes. Only process 2 and process 3 will just call MPI init. They will determine their rank, they will determine the number of processes, and then they're going to call MPI finalize. Okay, so that's waste of resources, but my application at least works correctly. So the original suggestion by the generative AI team to say, well, okay, if I don't run with 2 processes, bail out, is actually the better option in this particular case. But I just wanted to leave it in, just to point your attention to the fact that you should take care that you don't make an assumption, maybe implicit, on the number of processes somehow. And in my code, the assumption which I originally made, if my rank is 0 else, is an implicit assumption that there are only 2 processes. So that's an easy mistake to make. That's why I wanted to very explicitly do that. Okay. All right. So that was quite easy to do, but a little bit boring, of course. Okay. The tag here is also 17. So that's probably why I picked up that habit at some point. Okay. So basically, interesting. Here there's also an else. I'm pretty curious. Okay. That's the implicit assumption. Okay. Let's not go here. All right. Now we can extend that a little bit because typically timing a single ping isn't going to give you an interesting result for 2 reasons. One, this timing is not really, how shall I put it? It's not really deterministic. It might be that at some point you get a certain timing of a number of microseconds, and when you do it a little later, you get different value and so on. So first we need an average. And then the second point, and that is something which is very specific to MPI. So basically, the first communication typically takes longer because of routing information trying to be determined and so on. So typically, your first few pings, or the first ping at least, will take considerably longer than the next ones. So if you just time a single ping, you will not have anything that is statistically significant. So that's why we want to actually wrap that in a for loop. And what we're going to do is first, well, this is way too fast, sorry, wrong button. What we're first going to do is to answer. So we're going to have a ping and then a pong. And that, of course, is also a better measure, because remember, MPI send, well, this can be synchronous or not. So I'm not quite sure how long it's going to take for this message, for this MPI send to end. Is it waiting for acknowledgement or not? I don't know. We didn't specify that yet. So on the other hand, if I do a ping followed by a pong, then of course I'm quite sure that if I measure that time interval, that I'll actually have 2 times it takes 2 times the time it takes to send a single message. Okay, so let's do the pong as well. So let me do that one in C. So ping pong in C. Also I need some of receive buffer. I have source and destination here. Okay, that's interesting. Okay, automatic code completion and generative AI might be not your very best friend for MPI, because finalize with arguments, that's an interesting one. That's something I've never seen before. Okay, whatever. So, okay, all right, that at least is good. So if, and in this case, I'm just going to check for 2 processes and be done with it. Just simplifying things a little bit, doesn't matter. Okay, and then if my rank is 0, I have the MPI send. Oh, you just a send, please. Using the send buffer address. Don't forget the address. It's a single one. It's an MPI int, and the destination is 1. Okay, and I also have to initialize the send buffer, and the send buffer is not 1 but also my rank, just as in the Fortran example. Okay, so that we have, and this should be source. Okay, so it should be destination. Okay. All right. So that was where we were. Now I can just use an else because I know I have exactly 2 processes. So I don't need to check whether it's indeed rank 1. If it's not rank 0, it is going to be rank 1. Okay, so basically this was what we had. in Fortran. Also going to wrap my code a little bit. All right, and all right, so this was where we were. So this is the ping in C. Now we want to add the POM. So basically that means that process 1 now is going to send. Okay, so basically send buffer is going to be my rank. Okay, destination is going to be 0. Okay, and MPI send of send buffer to destination with the same tag. Okay, so that is the POM being sent. So now in process 0, I need the POM being received. Okay, so that means the source is 1 and MPI receive. Okay, and I'm also going to print that. Okay. All right. So now I've got a ping pong. Okay, let's see whether it works. So we save MPI CC ping pong. Okay, MPI run minus NP4. Okay, it bails out with the abort, so that's fine. Actually, I could have just checked the size in rank 4. Now I get 4 times the error message, but okay, never mind. So error handling works. Then a.out. Okay, process 1 received 0, process 0 received 1. So indeed, our ping pong actually succeeded. So that's good. All right. So then now we could time that, but again, that doesn't make much sense because that would be too short anyway. So here's an example where you would send the POM with a different tag. Okay, then you just have to make sure that the tags on the send and the receive match, but you can do that if you like. It doesn't really matter. In this case, I didn't bother to do that. Okay. So this is the code essentially, which I also just typed in. All right. So what you shouldn't do is overtaking. Messages don't overtake. So if process 0 sends a message, let's say with a certain value, and it sends a second one to the same destination, then it's always the case that the first message which was sent will be the first to be received. So overtaking is not an option. That's the MPI specification says that messages will never overtake, so that really should not happen. And essentially that is guaranteed by the MPI specification. So if you write an MPI library, you must somehow make sure that that is not the case. Okay. Now, that is true if both messages have the same tag. If they have a different tag, then of course that doesn't really come into play, because then I'm receiving a message with a certain tag, and I'm going to receive the first message from that source with the tag, with that same tag. If meanwhile If that was the second message which was sent, it doesn't really matter. Because of the tag, you can distinguish with the tags. So that is something that tags, for instance, are useful for, to make sure that you can receive messages in a different order than they're sent, but only based on the distinction between the tags. So that is one thing for which they can be useful. So what you can also do is wildcarding on the receiving end. So if I have an MPI receive, I don't have to specifically say, okay, it's going to come from this particular source. I can say MPI any source. And then I'm just listening for any incoming message from any source. Okay? And I can do the same with the tag, MPI any tag. So then the question is, okay, maybe I want to know who actually sent the message or which tag was actually used. If I want to know that, no problem. That information is stored in status. That's the envelope of the message, and that will contain the source, and it will also contain the tag. Okay, so let's go there. So basically, the message envelope is defined here. So basically, MPI status, then you have MPI status source, and MPI status, status MPI tag, status MPI source. Okay. MPI error we don't use, but basically it's a structure, so you can access the fields of that structure. In Fortran, similar thing, it's a user-defined type. So essentially you have status, percentage MPI source, status percentage MPI tag. So once you have the status, you can actually just retrieve that information easily. In Python, you actually, if you have the status, you actually can get source and you can get tag. So it's similar. And you also can get a count, but that's not a field of the struct that you can access directly. If you want the count, you have to use MPI get count with status as the argument. And that will give you the count at the receiving end. Why that's useful? As again, we will see later. Basically, it has to do with the probe functionality of MPI. Okay, so basically, here is the MPI count. So you specify the status, you specify the data type, and then the integer here, the count, that's an out parameter. Similar for the C interface, count is an out parameter, so it's address. Okay. Then there is a get count function, but again, you would have to specify the data type. All right. So this was a very straightforward example, but things get a little more complicated when we take different communication modes into account. So in fact, there is quite a number of these MPI send procedures. There are in fact 4 of them. So you have MPI S send, you have MPI B send, you have MPI send, and you have MPI R send. So they come in 4 flavors. Okay, but for all the modes, the corresponding receive is just MPI receive. All right. So this is all useful for different use cases. So the MPI S send is actually a synchronous send. Remember what that is? A synchronous send is not going to terminate before the receive has been posted. Okay, so that's that will give you the confirmation that the receive is actually in progress. The B send is a buffered send. So essentially that will return immediately, but it's going to use a buffer to store the value you're sending safely. Then we have MPI send, which we've been using up to now. And in fact, MPI send can choose at runtime whether it's going to send synchronous or asynchronous. So that's what I implied when I said, okay, we don't really know what MPI send is, whether it's synchronous or asynchronous. Yeah, we're never going to know, because that's exactly its definition. At runtime, it can be either synchronous or asynchronous. That is defined by the implementation of the MPI library, and that can, for instance, be determined by the message size, by the count. So basically, with an MPI send, you're not sure what happens. And then you have an MPI R send or a ready send. Okay, this is a really, really dangerous one. That basically means that you, as a programmer, are sure that the receive is already in progress. So this is a very dangerous one. Okay, so a bit of a summary. In the first column, we have the send node. In the second, we have the definition, and then some nodes. So synchronous send is MPI send. So basically, it only completes when the receive has started. That's what you know. Okay. Then the MPI send, B send, sorry, MPI B send. That's a buffered send. So basically, it's a local call. So it will complete immediately, unless something happens, of course. But basically, it doesn't wait for confirmation that the receive has started. So that's the difference between these two. Okay. But you need an MPI buffer, and that needs to be attached. Okay. Then MPI send without anything else is either buffered or synchronous, one of the two. And it will use an internal buffer if it uses a buffer send. So it will take care of creating that buffer, of disposing of that buffer, and so on. That is done by MPI send itself. And then the ready send, you can only start that if the matching receive is already in progress. So the node is highly dangerous, and indeed that is the case. So the question is then, why do you have this highly dangerous stuff? Okay, the MPI receive, it will complete as soon as a message has arrived. So basically, yeah, it's quite obvious you can't proceed from a receive unless you got your message. And there's only one receive. So 4 send nodes, 1 receive node. Okay. So rules. Why do you use one or the other? MPI send, basically, it's intended to give you minimal transfer time. So at runtime, the implementation might decide on one of the two in order to optimize the transfer time. Okay, so it can block. If it's for some reason synchronous send, MPI send is going to block. You know that. Okay, and so basically, it has all the risks of a synchronous send with respect to deadlock, and we'll see some later on. Then we have a synchronous send. There is the risk of deadlock, that's for sure, because I'm waiting until a receive has started. If that receive never comes, I've got an issue. Okay, you can get serialization. You'll see an example of that later. And you have the risk of waiting for that confirmation of the receive to arrive. So this can lead to waiting times and less efficiency. So it's going to likely give you a high latency, but it should give you the best bandwidth. Okay? Maybe, in case you're not familiar with the terms. If you look at communication, then you're interested in two numbers. One number is the latency, the other is the bandwidth. Okay, let's start with bandwidth because that's simple. That's just the number of bytes per second that you get across during your commute. Easy. What's the latency? The latency is essentially the startup time before you start your actual transfer. So that's the latency. So let's say that I talk at the speed of, I don't know, 45 words per minute. I have no idea whether that's realistic or not. Anyway, I talk at a speed of 45 words per minute, so my bandwidth is 45 per minute. Okay. Now, what would be the analogous of latency? Well, okay, I'm going to phone you. So I've got to pick up the phone and I've got to dial. That's my latency. Okay, so that also takes a while, but it's more or less constant for whatever I'm going to tell you. That latency is going to be the same. The time it takes me to pick up the phone and dial your number is going to be the same whether we will have a conversation of 1 minute or a conversation of 3 hours. Okay. Not quite that simple. Typically, in this context, the latency also depends on the message size. Okay. Why could that be the case? Well, basically, I have a buffer which I need to fill. That takes time. That's eating a bit into my, or adding to my latency. But okay, so that's essentially the idea here. Okay, then we have a buffered send. So that gives you low latency because the data just has to be stored in the buffer. And then the send routine, the MPI B send, can actually terminate, can complete. And somewhere the transfer is being handled. So that gives you low latency, but not necessarily good bandwidth. And then the ready send, basically it can be the fastest, but the problem is that you really need to be more than 100% sure that the receive is already in progress. Otherwise, the ready send, the MPI R send, will fail spectacularly, and your application will crash. Okay. So order preservation, we already mentioned. So basically, messages with the same connection, so on the same communicator, source and destination will never overtake. Will never overtake, depend if they have the same tag, of course. Okay, and that's true for synchronous or asynchronous sends. So it doesn't matter how you send them, the non-overtaking rule always applies. That's guaranteed. Okay, so basically, this I already told you. All right, then it's 1 o'clock, and I suggest we break for lunch. And question is, how much lunch break do we take? That probably mostly depends on the people in the room, but yeah, also online. So normally it would be 1 hour. Is this too long? Questions both for the people online and in the room. 1 hour is fine? Can be shorter? Any opinions online? 1 hour is fine. It was a question I haven't seen apparently. Oh, sorry. Normally I get a beep and I didn't hear a beep, so that's a bit weird. And it's a very old question, so I hope. Oh, it's not such an old question. Yeah, just an hour ago. Okay, so I see online 1 hour is fine. I hear in the room something like 1 hour is fine, but shorter would also be possible. Okay, let's make it 1 hour, just to make things simple. We just reconvene at 1 o'clock. At 2 o'clock if we do 1 hour. Okay, so let me put something here for the people online. Okay, then I'd say have a nice lunch, and I'll see you in an hour time.
Will you close the room or can you?
If you like, I can lock the room. Yes, no problem.